Yes. Good evening, everyone. A very warm welcome to all the participants and our distinguished speaker for the fourth day of our Atal Faculty Development Program on millimeter wave technologies. It's my pleasure to introduce our speaker of the day, Dr. Ashwin Kothari, Professor and Head of Department, Electronics and Communication Engineering, VNIT Nagpur, Maharashtra. Dr. Ashwin Kothari has received his BE and MTech degrees in electronics engineering in 1994 and 2005 respectively from Nagpur University. He obtained a PhD degree from Visvesvaraya National Institute of Technology, Nagpur, Maharashtra in 2010, where he is currently working as professor and head of department in electronics and communication engineering. He previously held additional charge as in-charge dean of IIIT Nagpur, which is an institute of national importance for the duration of 6.5 years. He is IEEE senior member and one of the coordinators for Center of Excellence of Combated Systems, which is a hybridization of communication and embedded systems under World Bank assisted project of TechWhip with a receivable of around 9 crores. He is also coordinator of recently established Center of Excellence of EMC EMI at VNIT, established with an investment of rupees 3 crores. He has several publications including SCI and Scopus and contributed book chapters for reputed publications to his credit. He has guided 15 PhDs so far and is currently guiding 4 PhDs. He has 5 granted to his credit. He was chair organizing committee of CVIP 2022, general chair of PCEMS 2024, and elected general chair of MapCon 2026. He is on the editorial board of many reputed international journals. He has 29 years of teaching experience and 1 year of industry. His research areas include image processing, antennas and wave propagation, electromagnetic communication, and rough sets. He has visited many reputed universities in USA, including UC Berkeley, UT Austin, University of Akron, and New Jersey Institute of Technology. He has 7 patents filed to his credit. He has worked on many projects on socio-economic relevance and has developed many working prototypes and products for assistive technology and other societal problems. A team of 5 UG students, guided and mentored by him, had stood fourth at All India level competition of Swadeshi Microprocessor Challenge, which is organized by MITI, Government of India, and coordinated by IIT Madras, and has won prize of rupees 20 lakhs and an incubation support for the product developed. He has delivered many guest lectures and keynote addresses. Apart from this potential profile, listening to all kinds of music, watching regional movies are his hobbies. He is associated with many social organizations like Gorakshan Sabha, Blind Relief Association, Outward Bound Bharat India, and Saraswat Mandal Nagpur. On behalf of VES Institute of Technology and all the participants from different states, we welcome you, sir.
Thank you, Gaurav, for the generous introduction. And that then defines a role which I have to be associated with to deliver my talk. So I will try my best. But at the beginning itself, I will tell you that the number of years or experience and research interest and all these are part of the biodata or so. But actually, I am still a learner and
True.
a team worker. So most of on varied topics I have worked and all, and this particular talk is very much focused on millimeter wave technology. So to tell you promptly, like the entire audience, that millimeters we have started working from last 2 to 3 years, and therefore there are certain related aspects around it which are to be known first if you really want to be a researcher or a learner in millimeter wave technology. So, like a ladder, we cannot climb the first floor without climbing the required steps of the staircase. So, it is that similar to that kind of thing. So, my today's talk will cover various aspects of it and all. Now, shall I I will have to go for presenting this thing, I think. So,
Yes, sir.
yeah.
So today's topic for Sir's talk is millimeter wave component design and applications. So over to you, sir. Thank
Yeah,
you.
thank you.
Yeah.
Is it visible, my presentation?
Yes, sir. It is visible. Can you put it in slideshow mode?
Yeah, just huh.
Sir, you can press F5.
No,
F5 key. Yeah.
that is okay. Are the slides changing?
No, sir.
No, sir.
Okay, I think I will have to go for entire screen. Are the slides changing now?
Yes, sir.
Yes,
Yeah,
sir.
yeah. Okay,
Anuradha or Manisha, just unpin sir, no, so that the screen will be maximum.
okay. Now I hope I am audible and the screen is also visible.
Yes, sir. You are
Yeah,
Yes,
clearly
sir.
yeah.
audible.
So actually, what happens when the topic for the talk is conceptualized and all, it's too early, like 3 months with for proposal and all we work, and that time some topic we give. So there is slight change actually. What is there is millimeter wave components when I am saying. So my most of the focus would be on the antennas in millimeter range. That also in detail I would be discussing 1 millimeter wave antenna design as a case study and how it can be used for sensing applications for concealed threat detection and all. And basically, prior to that, some RF or microwave range antenna designs and its aspect I will cover to show you that gradually, like if you are designing in this particular frequency range, how your design how your maturity or technical maturity as designer evolves, and how the same techniques you can scale up and apply it to the millimeter range and all. So to show how simple ideas work and they basically give you the outcome which is desired and all, I'm discussing those case also. So purely the components, if are said like precisely millimeter wave components, cannot be discussed all of them in such a stipulated short period of time, but still we will go through various issues and challenges and what can be the recommendable remedy over it and all that we will see. And title is not covering, but I will be covering a slight aspect of application of AI ML also into this particular application, because when it comes to design of millimeter wave, there is a hell lot of scope for optimization and precision and decision making and prediction and all for beam steering or various kinds of application of or RCS reduction, for example, and all. So that generalized discussion also as a future trend or scope for research we will discuss for some time. So this is my department where I am right now sitting and delivering the lecture and all. And as far as before I start with my formal talk, I will just take your 2 minutes to show you the collaborative opportunities of research and all. So basically, VNIT as together and EC a part of it. If you collaborate with us, we have Center of Excellence in Combated System, which is hybridization of communication and embedded system and set up with the TechWhip grant of 9 crore from 2013 to 2022. So we have many high-end equipments under this, wherever the product prototyping, development, or testing in the field of embedded system is to be done. We have Center of Excellence of EMI also. So complete pre-compliance test setup with anechoic chamber of size of 30 feet by 17.5 feet by 14.5 feet tall, and quiet zone of 5 meter, and frequency range from 1 megahertz to 40 gigahertz. That particular range we have. We recently have received a use case test lab for 5G also. The government has given 100 such labs. So for sufficing the need of this particular region, VNIT has been provided with one. We have Center of Excellence of AI/ML. Then we have IV labs, under which various sensor-based robots are designed and all. And quite a good number of students are involved in sensor antennas also, in particular this lab. We have Space Technology Incubation Center also by ISRO. So that is also a very good platform for going for collaborative research or things like that. We have Vishram Jandar Siemens Center of Excellence and Center for VLSI and Nanotechnology. So these are the glimpse of some recent facilities in the department which we have completely prototyping system or pre-compliance test setup, or you can see the picture of the anechoic chamber and its test facilities and all. Secondly, VNIT, you can collaborate. Those who are not PhD, they have under 10 categories of admission: part-time, full-time, working, non-working, whatever. You can get the guidelines on the VNIT website, and or you can have the internship opportunities also, your students and all, or you can work as JRF, SRF also. And as far as courses are concerned, we deliver a degree of BTech EC at UG level. We have one regular program of MTech Communication System Engineering, in which one vertical is of MMIC design, then antennas, particularly radio frequency circuit design and EMCMI. Then we conduct skill enhancement courses also under the Center of Excellence of Embedded System. And in online mode, we provide 2 degrees MTech program in Applied AI and Applied AI and Communication. And you can go to the departmental website and see the list of the skill enhancement courses. So if you are a teacher, it will add age to your deliveries. These are completely hands-on, and the highest fee is 4,000 or 3,500 only. These are 30 hours courses which we conduct in various areas. Starting with my formal talk now, as far as you see, I have gone through the schedule, and there are so many already lectures given on the basics of millimeter wave technology, what frequency range and all. So technical definition, we always give that it is a frequency range lying between the microwave and the extremely high frequencies and all. So basically, theoretically, we define it from 30 gigahertz to 300 gigahertz, where we at the starting frequency of 30 gigahertz, we get a wavelength of 1 millimeter. But if you see IEEE standardization, or even in Chinese literature, if you refer and all, you will find that every research has a trend. Typically, if we talk about the 5G millimeter wave band also, then you will be surprised that the frequencies below 30 gigahertz, which are in the range of 24 gigahertz or even the 20 gigahertz and so, have been used and are referred as millimeter wave frequencies only. So jokes apart, many times like I say that okay, whenever the frequency, if you convert it into wavelength and can express it as few tens of millimeter, then it's a millimeter wave communication. So typically your ISM band frequencies of 2.4 gigahertz or 5.8 and all won't come into that. But surprisingly, some literatures under millimeter wave communication also even mention frequency applications in X or C band or this thing also, whereas actually it would be in the range of 50 millimeter or so, but that becomes quite high. But then what we can take a gist from it, that millimeter wave communication when is there, I myself have found that typically it can start from 18 to 19 gigahertz or onwards or so, or wherever you can express it in up to 10 only, the wavelength. Now, microwave or high frequency or RAF or MM itself, in current scenario, like any of this frequency range you take, the general challenges which particularly we are or we will be facing would be the performance needs to be wideband. So bandwidth demand is always there. And antenna inherently you will find that as a component, microwave component or circuit or transducer, whatever say you, it is a narrowband device basically, and therefore to stretch its performance over a wideband or ultra wideband typically for any application becomes a great challenge, and therefore this can be a one generalized challenge which anybody can face for various applications. uh, we then you will find that the bands of the frequencies are continuously evolving. If you buy a smartphone of 3G, 4G comes. If you buy a phone of 4G, 5G is in offing and all. If it is 5G, then research of 6G already has started and all. And 6G, 5G, as I have said, the band mentions frequency about 24 gigahertz, even goes up to 120, 150 gigahertz or so. So what is happening is continuously the high frequency band or spectrum is evolving and getting formalized or included into the research as well as applications. And this finally results into a burden of high data rates or speed of communication which are required. So we want download speed very high, and the applications as such, if you see communication applications are getting loaded with media overheads and all, video, audio, whatever, or so many dimension video and all like that, it is there. Then interference, this is again another challenge which we are facing, because you see the compactness of the device would depend on the physical dimensions of the component, and it's a straightforward law: as frequency increases, naturally wavelength reduces, and therefore realization physically the component becomes a great challenge. And when they are of such tiny size, for a compact device, multiple devices will get fabricated into one assembly itself, and they would be working in vicinity of each other at such high frequency. And therefore, there would be lot of mutual coupling, EMI, EMC problems, and interference and all. As I have said, the design needs to be compact. Just if we take example of a mobile phone, no one wants it to be bulky or thicker and all. Sleeker the design, more it will be preferred. Then you will find that the geometries or shapes also are becoming complex as these applications are there. So typically what you find is, if you go higher and higher in frequency from microwave, if you shift to millimeter wave and all, then as frequency increases, even if it sometimes in some application goes into terahertz also, you will find that its use will be less in communication and more in sensing, imaging, this kind of applications, or even in defense applications also, where you have to identify the friend and the foe. And therefore lot many advanced equipments or warfare equipments or gadgets would be used, right from the missiles or you see the high end application aircrafts and all. And uh, to simulate these things, you will find that their geometry or working shape and all are very complex, and it is full of uh, containing different materials having different epsilons and all. And the radom designs or things like that will need even the surfaces to be conformal, means in a bent manner. So if you will need an antenna which can get bent, or array completely should get bent and all, so that we can fix it on the surface of the missile and all. Now this is not easy. This poses lot of challenges at millimeter wave communication if you want this kind of results and all. Then adherence to the standards, this is again another problem. So medical applications, imaging and all, as I have said, if you go to millimeter range and all, you will you will get yourself slipped into various applications of biomedical or this thing, and in most of it the devices may enter into variable category. Now if it's a variable category or body area network based devices and all, then the standards or safety standards or the EMCMI standards, to meet them is quite a great challenge, because the device is small, frequency is higher, and therefore thermal instability is the highest this thing, and therefore human tissues are vulnerable to various kinds of radiations and all. So that's why the organizations like WHO, that is World Health Organization and all, they come out with a specific absorption ratio limits and all, which we have to adhere. So these are the general challenges. Now these are applicable to microwave, high frequency, millimeter and all. So if we shift to the basically millimeter, then first we should study the trade-off that, okay, if we enter into millimeter wave, typically antennas as a component to be designed and all, what kind of benefit finally we would get? Is it only physical parameters like reduction in size and all, or there is something else and all? So the first thing is the high data rates and bandwidth. Basically, if you are going to get that, this itself is a uh, prime or so the most important factor where you will be happy to trade off for millimeter technology with high data rates and bandwidth and all. So basically, at this frequency range, it's obvious that you will get a very or humongous bandwidth basically, and the data rates would also be quite encouraging as far as speed of communication is concerned. As the wavelength reduces, the size of the device or the components obviously will be very compact, but that pose another challenge, what that we will see. And then high resolution and precision, this is very important. Applications like radar and all, where you will find that the by natural this thing process or at this frequency, you will find that inherently the beams are of narrower beam width and very sharp, because of which you will find that the beam steering or beam formation or beam control is very precise. So if it is given power of good signal processing algorithms and all, then you get wonderful results as far as the precision is concerned. You get very high resolution also, and therefore precise control also is obtained for that communication or any kind of application. It might be imagery, radar, or whatever it is there. So basically you will find that if you are in millimeter range, the resolution and precision is quite high. Then what happens is all of a sudden you are shifting to a band which in general is not overlapping or common with the other standards of frequency and all, and therefore automatically you get very reduced interference. It is like allotting a separate room which is not connected with any other room, and therefore you don't get any disturbance or noise and all. So naturally, suddenly if you are shifting your applications to a frequency band which is not overlapping with the ISM license free bands or other microwave frequency range and all, obviously your interference will get reduced. Okay, but inside the gadget itself, if multiple components are there, then interference again would be a problem. Secondly, what happens is as the beams at this millimeter wave range which are formed are very narrow and precise, therefore what happens is automatically you get enhanced security in millimeter wave communication, because the intruder to intercept these signals at this decibel range and all at this frequency becomes almost impossible. And therefore the, as we say in other case of communication, that frequency modulation has inherent noise immunity compared to amplitude modulation. Same thing happens with this thing also. So there is an enhanced security as far as this particular case is concerned. So millimeter wave gives you enhanced security. Now if you see at all these features, naturally you will be tempted to go for millimeter wave designs or components and all, because in today's world bandwidth, data rate, and enhanced security and precision and resolutions would be the, or compact size, all of them, like which one to pick up and make the trade-off and all, we always will be confused. So we see all these points or parameters are of prime importance and we always will be attracted to go for it. But in technology, nothing is best or worst. It is always a trade-off, and you get some good things at the cost of some other things that is there. I hope I am audible. Am I audible?
Yes, sir.
Yeah. So what happens is the moment you get these benefits and all, they pose the design challenges specifically for the millimeter wave antennas or components or whatever you are designing and all. So first thing which you will face is the propagation loss, as the, you will find that the penetration capacity of these for materials like building and folio and all will be very less. Their range is less and all, and therefore the propagation losses, they suffer a lot. as far as millimeter wave communication based millimeter wave based communication is concerned, then you will find that you will have a lot of material limitation also. The generic things which you pick up and design things for other frequency ranges, the same things cannot get picked up here. In millimeter wave, you have to be very thoughtful. The choice of the material is very crucial. You have to think about lot many things, that how is the thermal stability of the material, as a dielectric or a substrate, how good it is, or as a metal, how good conductivity it has at that particular frequency range. So you will find that these go on limiting the choices of material which you can use. And as your material becomes very specific or unique, immediately it will increase the cost, which I have listed downside, or uh, third from last. So automatically the material limitations result into design limitations, and the cost consideration, or that balance between the performance required parameters and cost involved, have to be given a thought. Then third is thermal management. This is very important, because anyhow you will find that the radiation intensity of any radiating body is directly proportional to frequency. And that is how we employ carrier of higher frequency in modulation or communication and all. So here what will happen is, as you are working at very high frequency, therefore you will find that the material which you are using, what kind of stability it has at that frequency, we should see. The size would be very small and all, and therefore it can make the entire component or device thermally unstable. Therefore the dissipation allowed, like for example, if you are designing FSS, or if you are designing it as an absorber. Now when we say absorber, means its job is to absorb the waves. Now we have studied very simple principle, that energy can neither be created nor be destroyed. So when it is absorbing the wave, not letting it getting transmitted or reflected or whatever it is there, then where it is going. Okay. So naturally it will reside in the material in some of the other form. The other form, when we say, means it's none other than heat itself. And therefore if the material is thermally unstable, what will happen if its quotient related to temperature is very low, it will start melting or deforming, or if conformal array is there, it will get cracked and all. So if it is already used for missile kind of operation and all, the rampant environment would be there. So you can imagine that lot many defense applications will have so much high order challenges, and you need a material which will remain at that particular rampant environment very stable and giving the same performance. So if you think about antennas like dielectric resonators, which are liquid based and all that, it will all get vaporized at that temperature and all. So that's why it is not that easy. Then manufacturing precision. Now here I will give example of weighing application. If you are weighing coal in tons, 1 kg, 2 kg here and there absolutely doesn't make a difference. But if you are weighing gold, then what happens? You might have seen whenever you go to the jewelry shop and all, or give some old ornament, they rub it and even they pick it up every minute particle which has been there, because it is useful and very costly. So here what we see, that the precision required is very high in smaller applications. So at millimeter wave, your manufacturing precision is great, because at that high frequency, one small change or deviation in the frequency will make a large change in the wavelength, and that it won't remain compliant with the dimensions or the resonance or whatever you decided as far as the performance of the device is concerned, that will get disturbed. It will get detuned and all, and therefore manufacturing precision required is of very high order. So when it is of very high order, that's why wristwatches are costlier than the wall clocks, because their intricate designs are involved in that. When you say manufacturing precision is this thing, you will have to go for processes like photolithography and all, which are costly, and therefore automatically the cost considerations will also come in picture. Then in microwave range or RF and all, the integration of the component is very easy. But in case of millimeter wave, the integration with other components is very difficult. So if you decide that a waveguide or strip line is there which is feeding, and that has to be connected to an antenna, this particular connection or feeding itself, which otherwise would have been very easy for other frequency ranges, for millimeter wave it will be very difficult, I am telling you. Therefore integration aspect is very, very important. And once antenna is a radiating body, or particularly the surfaces of which have been designed as filter, or FSS are to be used as absorber, or whatever it is there, the beam forming, beam steering is very complex, and they always need support of some kind of very good algorithm, signal processing algorithm. So it can be a Esprit, music, or it can be nature inspired optimization algorithm also, which can be used to precisely place nulls in the required pattern, or the peak, having peak at one particular position, or having the desired radiation intensity or high directivity which is required for the application and all. So if you want now, what see what happens is, when you mention one parameter, it is at the cost of something. If I say beam steering requires an algorithm won't run in air. That means it will need computing platform. Means what has happened now, you were talking about antenna, now you are talking about smart antenna. So there would be a complete control plane, RF circuitry required for it. So there would be upscalers in the frequency which will come in picture. We will need very high speed analog to digital or digital to analog converter, which are doing the job in real time sense, supporting the entire beam formation and all. And it will be completely a closed loop system, which will involve lot of complexity and all together to be inserted into a compact device or gadget typically. And then that computing should be power efficient also. So it's not that easy. That's why I am saying that the earlier slide if was showing all the advantages, but they are at the cost of these many overheads. And then environmental sensitivity, as we say, the millimeter waves are very sensitive to rain, fog, dew drops, and highly get attenuated or severely get attenuated with the change in the meteorological conditions, or they are very, very environmental sensitive. And with these small size components and all, if they are so sensitive, what is going to happen is nothing but your device performance will be vulnerable to even slight changes in the surroundings or the environment and all, and you will lose the essence of the application. And therefore when things like antenna at millimeter wave, or the components, other components, amplifiers or filters or whatever, if they are to be designed in this frequency range, this environmental sensitivity you have to keep at first take itself, that in which kind of environment or for what kind of application typically this component is going to get used. If you are not clear about that, most of the PhD researchers, they say that we are working in millimeter, okay, this and that, very nice. Now where you will use it, they are clueless about it. And while submitting the thesis, then they go and do reverse engineering and try to map it to some applications and all, and then they miserably fail. And then they come to know that we are linking it to missile, but the first basic question can be, but missile will be at this temperature, the substrate will melt. Have you not done that analysis? It is very sensitive to the environment in which it is going to work. So then your claim is false. So therefore you will find that when such type of designs are to be done, these basic thoughts must be taken well into account and all. So which kind of millimeter wave components typically we can go for? So they, on a broader way, include antennas, filters, amplifiers, power combiners and all, and many more types of devices. And various popular devices, the example can be given as like antennas are there. So the Coco antennas are there, which are omnidirectional, typically working in frequency range of 27 to 29 gigahertz. Or Hor antennas are there with dual polarization. Then there are low noise amplifiers or power amplifiers which are used for RF circuitry or supportive signal processings. Filters, typically the band filters with insertion loss or return loss of desired values are always there with millimeter wave. And then you can say that it is band stop, band pass, dual band, quadri band and all, depending on the application. Those kind of functionalities or characteristics you can achieve. So what you can then do, you can go for power combining or combiners also, which can be two-way, then with desired isolation and insertion losses like 15 dB or 2 dB respectively. There can be other components also, detectors, isolators, circulators, sliding match load and all, or you can see D-band power meter and all, or variable attenuators, fixed pads, or directional couplers and wave meters, and there are so many. Now, actually, these are not just millimeter wave component, these are general components, but you are using them at millimeter, so their characteristic and design altogether will change because it is scaling up in the frequency. So what happens is millimeter wave components, once you design, what would you do with them? So you can use in variety of applications, including of involvement in a scientific test bed or test and measurement equipment and all. So you will find that the highest application currently is nothing but in test instruments itself. So as the audience has registered for this course, means most of them might be having certain ideas about the measurements done for antennas and all. So they might be acquainted with the basic measurement setup, and also they must be knowing the devices like vector network analyzer. Okay, now this vector network analyzer or spectrum analyzers or signal analyzers and all, if you want the EMCMI receivers and all. So earlier you were working in this, and now you are saying millimeter wave, means you will require frequency 26 gigahertz and above, 24 gigahertz and above, or 19 gigahertz and above, and up to 90 gigahertz, or even terahertz also, 1 tera or this thing. So naturally, you see the principle of heterodyning, mixers, frequency mixing, they all remain same. What was there at the lower frequency, or even with design with components like BJT and all. But now only thing is the frequency has got scaled up to a very very large value, and therefore the type of components which would be used in this type of devices has to give precise and accurate performance for test and measurement. So therefore you will find that RNS or Keysight, Enritsu, these are the companies or generally vendors or OEMs which sell this kind of equipment. And you just ask for the basic model of VNA, which starts from 26 gigahertz and end up to 55 gigahertz, or upgradable up to 1 terahertz and all. And then you will find that the same VNA is there. It is only if you ask for 110 or any other kind of frequency range, they will just bring the module which will be connected to it, which will be a frequency multiplier, and the same device will start working on the higher frequency range. But you will find that for the cost for such small module or entire VNA, it basically starts from 2 crores and onwards, and then for every gigahertz or megahertz range, the cost will increase from 1 to 10 lakh and all. That's why the biggest application is test and measurement equipment and all. And the next, as I have said, that communication, if it concern, then industrial radars or wireless communication equipment it will be used. But one which is not mentioned in the slide, at this range it will go more into sensing applications, so as sensors, imaging and all, and therefore various biomedical applications and all will see also will be encouraging one to go for. So now what I will do is I will first cover few cases of the frequency ranges lower to millimeter wave, and typically just to show that how simple simple ideas at microwave or high frequency range, just a band which is adjacent to start of the millimeter wave and all can solve your problem, and how same techniques you can scale up and go for the millimeter wave designs and all. Now, these are nothing but collection case studies of most of my PG or UG or PhD students who have worked on various aspects, and they are now very successful and working at different places. And also, Anuvind is in the DRDO or ERTL, and Manoj Stanley, Sumin Joseph are the scientist at Liverpool University, and Chetan Wagmare is currently working in an industry in the field of quantum computing. So basically, in their PG project, the idea was that time or even now also, your gadget like laptop doesn't have a capability of software defined radio SDR or cognitive radio capabilities, where if whenever net connectivity is required, it can find out which is the white space in the license band and can transmit your data on the available white space and all. So we were in process of designing the black box, which we were thinking of can be connected or get connected to a laptop, and if it is there, your laptop will get capability of SDR or cognitive radio. Simple, your laptop will become a device which would be involved into spectrum sensing first. So entire spectra it will sense and find out the free license or unlicensed band which is available for the transmission. Then there would be an algorithm on priority, so a processing block which will allocate that particular white space. Then it will reconfigure itself, because sensing means it is receiving and transceiving rather. And then finally on the band which you have got free, on that now you have to transmit the signal, so you will need a ultra wideband transmission assembly also. So if this has to be realized and all, in that a total this thing black box would look like something like this, which will have a cognitive transceiver capabilities and all. So there would be sensing antenna which would give input sensing to the sensing monitoring circuit and all. And there would be a transmitter and receiver having transceiver capabilities. So you will reconfigure the frequency, and on the allotted frequency you will retransmit the signal. And then naturally, who will do the processing? So we will need the backup of sensing algorithms also. There are many sensing algorithms. So what we see, this entire project is not a smaller project. Actually it is equivalent to 3 MTech or 3 PhD problem statements and all. And then different modules were divided amongst them. So then our challenges started. So for implementation we were in need of some spectrum sensing antenna. Then if spectrum sensing done, then we need spectrum sensing and monitoring circuit itself, which would in turn run the sensing algorithms implemented on hardware as a backup control plane. And then finally on the other end we need one frequency reconfigurable antenna for retransmission on the allocated band. So clearly we can see here one antenna for sensing, another antenna, wideband antenna, for transmitting the signal on the allocated band immediately. If you come to know that this particular frequency band is free, then now this particular antenna should get tuned to that frequency and start transmitting the signal on that particular frequency. And therefore the entire thing would result into a reconfigurable transceiver. So we can say that this is nothing but equivalent to three projects. So they were divided like this, and one by one we will see how the implementation was done. So then it was seen that the spectrum sensing antenna requirement, particularly it is there, then we would need particularly ultra wideband antenna which can show a what performance from 3.1 gigahertz to 10.6 gigahertz at that particular time. This I am talking about 2019. That time the test facilities were not even available up to 12 gigahertz or so. And VSW are required in the range of 1:2, and return loss, of course, minimum minus 10 dB has to be there, and the radiation pattern should be omnidirectional. That was the case. So we went along the literature review and found that various kinds of antennas are available, but mostly the patch antennas would be more suitable. And with the lucidity in the design, if we just start with a very simple basic patch antenna which is circular in nature, what kind of performance it would be giving, and whether it would be ultra wideband and all. And then of course it was found that the circular patch simple antenna is quite limited in its performance to give these particular desired characteristics. So the work on it was done. So it was then supported with the finite ground plane on the other side. Then as far as you will find that it is a technique of staggered tuning. Basically, moment you add the ground plane, what we see that the particularly fundamental frequency and its harmonics become active. So we will get resonance at various frequency, and therefore the required bandwidth can be achieved and all. But at the same time it is to be used for sensing application, and therefore the copper loss has to be up to that value. And therefore we have to make a slot particularly in that patch and all, and therefore it gets converted into a spanner head kind of shape. and based on it, every simulation was showing that what kind of improvement can be there. The size optimization of the slot also would come in picture and all, and that is how the particular design got evolved and progress, and finally up to 9 gigahertz bandwidth could be achieved, limiting its performance up to 11.43 gigahertz. Now this, if you convert, you will find that it will come in multiple of few tens of itself, and the radiation pattern also were verified and all. Now these are the things which are up to simulation, and you can see 3.8 to even 11, this thing 0.43 gigahertz, the radiation patterns were encouraging. This range is quite high. Now if this ultra wideband performance from this patch can be obtained, and then it has to be verified. So from here the difference changes now. So it's not just the simulation was done or only fabrication of patch was done, but we have, as we said, that we have a center of excellence of embedded system. We have National Instrument chassis PXI system, which can stimulate this particular antenna over a wide band range of frequency typically, and we can get its transmitting characteristic tested and all. So this is the complete NIPXI device, this thing based on which this spectrum sensing setup was there, and it was a industry sponsored particularly idea when this antenna was integrated with this particular setup. So those who want to do this kind of testing even now also are welcome. These kind of facilities are available. So this was done, and then even the time domain analysis of this antenna was done, and found that the sensing is quite done, or it can be, means this antenna can be very well used typically for this sensing and all. So the measured and the simulated results even could be seen, and then typically the return loss or on VNA setup also was checked and all. Then a RF completely transceiver circuitry was involved, because this block has to be realized. Then now actively this antenna has to sense the spectrum which is available. For that, a signal generator was used to sweep the frequency over this wide range and produce radiations on these different frequencies, and this spanner antenna connected with this RF transceiver module was expected to sense that particular spectrum. So you will find that this is a complete transceiver setup. So there are two antennas, one is this thing and one connected to the VNA to see the particular which tune frequency it is checking, or this thing, sorry, antenna connected to the sweeping signal analyzer. So sorry, arbitrary waveform generator, and therefore you will find that based on it particularly this antenna is really doing the spectrum sensing or not could be known. So this way it was completely tested and validated, and one part of the project was over. So it was found that this, but now the next job was to embed these sensing algorithms into this particular hardware. And for that, then it was found that if particularly various kinds of sensing algorithms are used, then cyclostationary or energy detection and all, which one will work better and all, those also were benchmark, and one of them has to be picked up. So you will find that this particular thing was again tested, and various algorithm where we tried to implement it on the FPGA, this thing where synthesizability can be tested and all, and then finally connecting it to the RF module to which this antenna would be connected, and then it would be tested whether really this thing has been taking place or not. Now when this is done, the three choices were available. One is energy detection, another is covariance sensing method and all, then cyclostationary, or which particular thing is there. Out of that, the I will just skip this NI part, the entire simulation system setup and all, and converting into a working hardware. And I will directly show you the results. So here you can see for a sine wave, simply we can see that the best performance is given by the energy detection method. So covariance sensing, cyclostationary, and energy detection. These were the three techniques particularly which were used, and the performance with this antenna for energy detection was found. When GMSK modulation was tried out, then Again, we can see energy detection is still working better. So like that, in case of other this thing, the cyclostationary has given the better performance and all. So like different techniques were used, but finally energy detection, because of its synthesizability and the lesser computational complexity, it was basically implemented. So second part was also the over. But now third part, which was very tedious, that if we go for such a wideband this thing sensing, which particular band or white spaces would be available. So we can see that GSM 850, 900, GPS, DCS, PCS or UMTS, these are the band, or LAN. Typically, these will be the band these antenna may sense as free band on which the retransmission can be carried out and all. And therefore, remember, that means you now need an antenna which can work from 824 megahertz to 2484 megahertz. So you want such reconfigurable very wideband antenna which can reconfigure itself for the available or free frequency for the cognitive capabilities, and on that can carry out the retransmission and all. So again, the literature review was done and all, and then it was found that amongst patch antennas, PIFA or planar inverted F antenna is the best one. PIFA is which one? Every one of you have mobile phones. Anytime, if possible, if it is not working and all, open its assembly and you will find that right from the FM connectivity to Bluetooth to Wi-Fi, and then your GSM connectivity at dual bands and all, or near RF connectivity. For every purpose, there is one PIFA antenna. So two gray blocks, one lavender, a third gray block, one green and blue. All these are nothing but the 6 to 7 antennas embedded in your mobile phone. So you can just imagine that many of you might not be knowing that there are multiple antennas are there. You might be thinking that the same antenna is getting reconfigured itself, but we know, we need simultaneous working of this thing. Means if you are listening FM radio, you want that your Bluetooth connectivity still should work. So this will be possible only if you give different antennas. And therefore, what is happening is different antennas radiating at such high frequencies. Now you think that in 5G capabilities in millimeter wave band, 6 antennas working at 24 gigahertz, such radiating bodies in vicinity of each other in such sleek design, if they work, what kind of mutual coupling they will have. So it's not a very easy design. It's a great design challenge. And these people have worked for years together to refine those designs and all, and have come up with very stable and less interfering or almost negligible mutual coupled antennas and all, multiple in number. So somehow some idea got struck to us, and for this reconfigurability, we came with one particular design that okay, instead of one PIFA, we will have multiple radiating elements connected together with active components like pin diode and all as switches, and we will have two E section, one I section and two C sections, based on which particularly this kind of antenna we would work. And what will happen is, like, there are D1, D2, D3, D4, D5, D6, six diodes are there. So 2 to the power 6 switching combinations would be available to get combination of radiating arms of this particular antenna. And therefore you will find that if it happens, you will get different radiation patterns and frequency ranges on which this can work. So initially, naturally, the materials are very costly and all. Now this antenna, if millimeter wave, if it is to be designed, the immediately the limitations on the material choice will come. But that time it was designed with FR4 with 4.4 dielectric constant and all, with thickness of 0.8 mm. Can anybody just put a guess that this idea is influenced by which particular simple component? Actually, this is just to demonstrate that when complex or complicated designs in millimeter wave, if you are trying, you may get solutions influenced by the simpler ideas. So out of audience, can anyone just tell, like, this is based on what? Actually, multiple radiating units and then switching, where this idea from where it gets influence? One such simpler component in our everyday life, as far as electronics is concerned, we know it, but we never thought that that concept can be applied to antennas also. Can anybody put a guess or tell? Come on.
Yeah, participants can unmute and answer if they know the things.
Okay, I will answer it. I thought that the idea might have struck this. This is just based on 7 segment display. Okay. So you already know in 7 segment display what are there? 7 LEDs are there basically. And whatever character we need to form, we actually make that particular part or LED or part of that LED active basically, and then we can generate 0, 1 alphanumeric characters we can generate. So from there we got this idea that for reconfigurability of the frequency and reconfigurability of the radiation pattern over a wideband typically, we can use this kind of concept and get antenna reconfigurable. So from that simpler idea, this came simulated and all, and then you can see that every possible frequency right from ISM license free 2.4 to 5.7 or 8 7.9 to these like scaled up, and you can see 000 or 111 means what? They are the combination or switch combination of those pin diodes. So all off, all on, first off, like that. Now you make a truth table and go on analyzing the radiation patterns or current distribution at different frequencies by controlling the switching of the diodes, and you will find that this is the actual photograph or picture of the fabricated this thing, the test result and all. And then we could find that you can see here the range like this which it has gone. Now again, this particular project was done 6 years back or something like that. Now you take the material which is available right now, apply the same idea. If that time it can go from 1.5 gigahertz to 8.18, why currently it can't go up to even 30 gigahertz or more than that, or 26 or whatever it is there? So easily this idea is applicable to millimeter wave communication also. Only thing is, one word of caution is here, your size would reduce and typically it will become very small, and therefore the other intricacies will come in picture. But if the design challenges posed in millimeter wave communication are to be made, what kind of ideas basically you can put and all, to show that I have shown this particular example. So this was then all finally now the integration coming together. So the spectrum sensing with PXI chassis based on it, the RF transceiver model and all, and then LabVIEW coming into picture and controlling the software defined capability of the processing block and all these things taking together, finally we could come out with that particular black box, which was really giving the cognitive capability to our this thing. Now only thing is, what will happen is, if you now try to convert it at millimeter wave range particularly, then you will find that you will have to go for MIC or MMIC designs kind of concepts and all, and lot of intricacies would come in picture. But to trigger your mind, I am first showing the other frequency range ideas and then how they are implemented. Now this is a crisp millimeter wave sensing applications which is designed with the zeroth order antenna, with the help of all such influencing ideas and all. But before we go directly to this particular project, if biomedical applications are there and all, what kind of precautions you people will have to take and all to decide that? We will first one discuss one project and again we'll come back to this millimeter wave design, range design again. So you will find that for certain application it was required again to go for a compact UWB antenna with integrated triple notch band for wireless body area network applications and all. Now these are variable one. When variable body area network you are talking about, then you have to face lot of challenges, right from the who specified specific absorption ratio and meeting that and all. So therefore again you see the UWB spectrum, then challenges were meeting at this frequency of 3.5 or 5.0 or even going up to 10.6 and all coming into picture. Again same thing. So patch antennas were there. So A, you can see simple patch antenna is there, then one stub is put, then two stub has been put and all. And based on that, when stub has been put, basically what kind of electric capability or resonance or we can say multi-band resonance it is giving to the antenna and all. So finally that we can test, you can see the compact size of the antenna, the current distributions and all, and how the design got evolved. And basically you will find that with one stub, two stub, the proposed design of antenna can be verified or tested also, right? Its evolvement from the basic structure. So it's not just trial and error, and also all these antennas were actually tested on the goat meat for regenerating the functionality of human tissues and all. And when you are working with this kind of antennas, you require permission from the Medical India Counseling and all. Then authentic subjects are required to check the things and all. So it's not that easy. Just to make or give a word of caution, even the medical imaging or imagery sensing antennas which are designed in millimeter wave when are there, you will have to follow all these procedures basically, and you cannot give your crude result. Now, based on this, I just want to show here that during COVID, one of my BTech student, she alone did one project. Actually, she was working with antenna for some other applications. But how an idea got triggered when she was measuring the return loss of the antenna, that particular frequency range, and due to the holding of antenna, as she changed the gestures and all, there was lot of variation in the return loss of that particular antenna, and from that she got an idea, and she basically designed one antenna which can be used as a sensor for human activity classification. So the entire idea was to have a particular flexible antenna, the data set collection particularly on various subjects and all, and then you will find that its analysis and finally on phantom can be tested and it can be done. So this was the particular experimental setup. The human subjects were there. They were asked to wear the variable antenna, a variable antenna on their arm and all. And for different subjects, they were tested. So there also we tried many designs. That there were like three types of prototype were there with various types of material. Some were rigid, some were what we can say flexible enough to get wrapped on the arm and all, like that it is there. So this polycap, the material and all, they were also used. And with this, these were the subjects, and different gestures were tried. Simple VNA to just measure the return loss with different gestures and all. The data set collection was there, and the results which we got were surprising. Then we like could find that you can see here the two slides, or the results I have added for all the four prototypes basically. And what they can show is typically every antenna has a designated uh, pattern of its measurement for a typical or particular action only. So if you take antenna 1 and do boxing, you will always get this pattern only. If you take antenna 1 and do clapping, you will get this kind of pattern only. So you will find that the patterns are designated with the type of the antenna and the action also. This we can know. So boxing, then again clapping, and but if the antenna is changed, so these are called as signature patterns of the measurements which you are getting for every action. We are with different subjects you are trying. So 10 subjects were there, and you can see all 10 subjects are almost coinciding with each other, whatever variation in measurement is there. So this is for a neural network, very interesting data can be there. Now see antenna on one side, connecting it with neural network and all. We develop this algorithm typically, and a classification, this thing application can get developed from this particular antenna, which is based on the Euclidean distance, and based on this the complete confusion matrix or percentage of accuracy can be derived and all. And therefore you will find that we have tried that particular thing, and then it was successful attempt, and this BTech student can come out with 2 SCI publication at her BTech level project basically, just because of this very novel idea and all. Now recently she is doing masters at Texas University, TAMU or A&M, and is working unfortunately in the field of computer science. Though she was having a strong background in electronics and all, she was offered PhD position also at ISC Bangalore. So what I'm trying to tell you is that if you get a if you give a thought process, do the experimentation, then you will get lot of idea whether it is millimeter or microwave. That really doesn't matter. Okay. So now based on this, we will again, as I have said, go back to the project which is in the millimeter range, and typically how that sensing application was achieved as per as zeroth order antenna was concerned, so we will go for that. So this again, this was a PhD problem statement which was very interesting, and it was basically concealed threat detection. So most of you might be Mumbaikar, so you might be knowing that this thing there was that 26/7 attack was there in the train and all, and the explosives were planted. So my PhD scholar Paritosh Peshwe, who happens to be now faculty at IIIT Nagpur basically and still working in this field and all. So we were thinking of, we read lot of literature and suddenly we realized that basically at certain frequency range which belongs to millimeter wave starting from 30 gigahertz gives very good response to the lidar kind of application for the wave transmitted and reflected back if they are received. Then the wave modal behavior changes if the material is explosive. So the idea was basically in a situation like train, the basic assumption was that this antenna based sensor won't be mobile. It will be fixed one, wired one. So there was no constraint of battery life and all. And basically we were in position, we were in desire of having a conformal array basically. So you can see there would be a central processing node surrounded with these nodes, and each of the node will have a conformal array sensor which can have 360-degree coverage around it and all, and they would be emitting waves in pulsating way, and they again will analyze the received waves and all, and these sensors in public transportation system would be fixed like this, and then finally these nodes will talk to each other, and then information will reach up to driver and all that, okay, in this compartment something fishy has been planted and all, like that it is there. Now it sounds interesting. This is a non-contact type of concealed threat detection, whereas explosives only can be worked out on the vapors based, so chemical nose can be designed, or even the other RF lidars are there, but electronic detonators can get triggered falsely if you use frequencies lower than millimeter wave communication and all. So that's why this is a very crisp application of millimeter wave or exploitation of millimeter wave. Now explosive techniques detection, if are there, there can be various technique, so neuron detection, x-ray detection, or this thing, but there are two main: electromagnetic imaging and non-imaging techniques. And basically imaging, they have a very these things bulky setup, as far as you will need lot of processing on images and all. So non-imaging technique, they needed of to be explored, that with this certain frequency range is it possible or not, and what are the relative advantages and disadvantages and all, like that, with non-imaging and all. That's why we can characterize a signal reflected by that these kind of materials, and it is less complex, and it can be extended to construct a sensor node based on it. That's why we decided, okay, then how much range would be there and all, and comparison about the techniques which are non-imaging one. And then we find that basically this IF based detection, or this thing technique, is quite encouraging and even gives you a range up to 20-meter also. And in the same table you can find at the bottom the millimeters, this thing principle is there, which is gives a lesser range of to 3 meters, but is very promising one. And therefore then the selection of frequency was quite crucial. So in which particular range it has to be, and therefore with the particular higher stand of distance and all of are required, natural choice was the millimeter wave, which standing in the range of 30 gigahertz to 300 gigahertz and all. So you can go for that particular band. Now when that was there, then it was next question, then in this particular band which frequency then. So typically the standoff screening, if you see from literature, we could know that there are two popular frequencies which are almost used every now and then. Among that are 30 gigahertz and 94 gigahertz, and that's why then we fixed 30 gigahertz. Now right now, from physics point of view, if we compare, there can be lot of advantages at 30 gigahertz and all, but at that time the real practical reason was, in entire India that time the measurement setup was not beyond 35 gigahertz. Our 26 gigahertz. Our own antennas, we had to send it to University of Liverpool, and from there the measured results we received. After that, care IIT Delhi and all, they went or upgraded their facilities to higher frequency ranges and all. So when we talk about design issues, challenges in millimeter wave range and all, always remember one thing in mind, that measurement setup or test setup will be the biggest challenge. You may take higher frequency, but your design may remain limited in simulation only if you don't have practical fabrication facilities and physical test bed facilities to go up to that particular frequency range and all, because these equipments are very costly. So you will find that that's why there we thought of 38, and then we realized that the detonators may get falsely triggered. That's why your flat profile must be followed by that electric vector or field vector and all. And if that this is required, then the antenna has to be zeroth order, means radiating in mode 0. So you will find that zeroth order resonance excitation, if it is required, then it would be according to avoid the ignition process of the detonator in the bomb and all, and there won't be any variation in the surrounding field, and there would be a flat field distribution which would avoid the accidental triggering of the thread. So the electric field vector distribution at that particular frequency range, different modes are there. So N1 or -1 or 0, and also you can see here amongst all mode plus minus, the top line shows the zeroth mode M is equal to 0, which is the basically flat field distribution in zeroth order resonance which was required. So this mode was then selected, and then we started. Obviously now the first choice was simple patch antenna typically, compared with the other benchmark. Now I think there is some goof up with the setting of the, I have changed the device, and these titles are getting overlap. I'm sorry for that. So basically we came out with this first simple design, and we tried to find out that at 30 gigahertz what kind of functionality it is giving us and all. And then we found that basically to enhance this thing, one interdigital capacitor finger kind of structure is required for having the desired gain variation, or this is basically again getting an electrical equivalent. If is seen, then we are going for a very good combination of series and parallel capacitors basically. So then the plain patch which was there, we we have engraved here the interdigital capacitor kind of structure into it, and immediately then we could see that the 30 gigahertz this thing matching characteristics were improved and all, particularly when this antenna as a load was connected. And that's why then it gave us that one hint that we can't move forward without this IDC structure which is made part of the patch. So we again went ahead, frequency was again fixed and all, but then it was found that the uh, uh, particularly the radiation pattern or the resonance and all due to capacity impact of IDC was studied and all. It was all good, but gain was not up to the mark. And secondly, if array is to be designed, the mutual coupling was quite high, because one antenna will cover patch in certain width only, say 60 degree, 40 degree, or 30 degree. And if you want complete 360-degree coverage around the node, then you have to make a conformal array, means a bent array or a round array of all such type of multiple antennas. Now the pitch or the spacing at which they will be kept and all was quite challenged, so we selected a quarter wave pitch with that, and first tested the design with an array of two elements only. The 5 rupee coin has been placed just to show you the compact size. Even the connectors are looking bigger than the antenna. So you will find that this kind of way the sensing this thing was there, and then mutual coupling analysis was done with this particular IDC array or this type of patch. And then again the result was compared, and then we found that still it is not that up to the mark what we want. So again, evolution or radiation pattern, can we increase this thing so that it can help us to have a better beam steering and control and all that we were trying. And therefore then we realized that from the current distribution, if it has to be there, the length of this each of the radiating element need not to be same, and therefore the, you will find that the current remaining confined with the IDC structure itself can result into more directive radiation pattern. If this is there, then scientifically they need to be of different length and orientation. And if it is to be achieved, then how to go about it? Like this digital capacitor, the fins need to be of different length and orientation also. So then this is possible only if we go for a staircase structure. So this then was again improved to a, or was converted into a staircase structure particularly, and then it was tested for the zeroth order, this thing, its analysis and electrical equivalence was tested and all, whether we are getting the flat field response for the electric field or not with mode 0. When this was done, all our problems were sorted out, and then you can see the finally evolved one patch antenna would have the digital capacitor integrated into it. At the same time, it will have staircase structure also, which provides us locally the orientation variation also, and at the same time providing us the different radiating length. And with this, then the results were quite encouraging. So the total omnidirectional radiation pattern analysis was done for one particular antenna. It was compared with the benchmark designs at the same frequency range. Now the next problem was to achieve 360-degree coverage, and also naturally you need to make an array. And how it will be a part of this entire system? So there will be the crystal oscillator, then power amplifier, then frequency multiplier, and the diplexer will first make the transmitter on. It will target the wave, sorry, it will transmit the wave on the target. The target will reflect it, the diplexer will switch on the receiver. There would be low noise amplifier, mixer, match filter, power amplifier, and the processing block would be there, which will do the modal analysis and will tell you whether the material is explosive or not. This is for one node. But then what is happening is, this is possible if this antenna is giving you the 360-degree coverage for tracking all the target around that particular system. So this would be the center coordinator node design. And therefore then this antenna needs to be a conformal array of all such antenna. So then question was how to make conformal array, whether it has to be with 5 elements, 6 elements. Then now you do on doing the direction of arrival estimation at this millimeter wave range antenna and all, and go on experimenting, finding the optimized number. Now I won't go into the mathematics of it and the pattern synthesis of this conformal array. So beam switching was also tried out, and at the same time signal processing algorithm were also tried out. Now here you can see at the bottom it is written 3 element. When the number of elements are varying, means with an angle of 120, 4 element means 90, because it is 360 required. Then 5 means pentagonal, 6 means hexagonal, like that it is there. And therefore beamforming and steering with this particular required side lobe level and things like that, the beam steering was tried out, beam switching was tried out, and the optimization was required. That was done with the help of this algorithms like particle swarm optimization, or you can even go for this sequential this thing quadratic programming. So you will find that these kind of algorithms, when are used, the desired beam and the resultant beam can get compared, and we can see whether the exact required steering is going on or not. So based on this, then finally we decided to get it optimized to 5 element this thing, and then we studied the issues in beam forming or beam switching, and finally came out with this and then have done even the mutual coupling analysis also, like 5 antennas working together, whether they will interfere with each other or not. So this is all mathematics related to it, and their CRLB performance matrix and all, it was done. And then finally the error estimation was done for the direction of arrival using music algorithm and all. So what I'm trying to tell you is that just one application at millimeter wave, the component design is there. The required functionality won't be effective unless you have supportive signal processing algorithm and all. So many of you who were thinking that I may do research in millimeter or work in that or this area, but remember, you will have to have the knowledge of these other fields also. Otherwise, how will you know that the required optimization algorithm will be supported by your end antenna or not? So this I am showing. So DOA estimation was tried out with different degrees of azimuthal and elevated angle and all. Now this is the close-up picture of the one node particularly conformal array with 5 such elements fabricated and all, and these node then are to be used as a sensor. And typically then this further process part was to add RF circuit and all, but since our discussion today is limited only up to designing of antenna at this millimeter range, so that's why I covered this project and have given the details here. Now the further extension are versions of the design and all, our team is working on that. But here I want to show that just one simple design doesn't end there when you are working in millimeter, because the frequency range is such high that at that such low wavelength this thing, there will be many intricate problems which will come into picture, which you will have to resolve and so on. Now, as we are coming to the end of the session, quickly I will go for the FSS based designs and all. If you want to go for the frequency selective surface, which is also one of the component at this range and all. Now, of course, the designs which I am showing are just touching that particular frequency range, but are not purely on millimeter, but ideas you can get right now, because for testing this only to achieve quadriband or stop band or dual stop band itself has created lot of problem. Now we will scale up the frequency in these designs and all. So for this FSS, this thing where the application was RCS reduction as far as defense system was there, and we needed it to be for multi-band and all. So therefore the fractal geometry was thought, and typically for C and X band, this thing with TATM polarization means both kind of waves and all, can it help us? So we started some designs here. So unit cell in 4 quadrant was defined, and we actually having an array of various length radiators placed with this pitch in some fractal geometry pattern and all, and therefore dual part this thing was made, and then finally from the same the array can be achieved, and the material used was giving even bend also, so we can do the bending analysis also of the same, so that if it has to be fixed into the radon of missile and all, radom of missile and all at the tip end and all, can we use this particular thing there. Okay, so this was tried, and this is the fabricated surface, and its actual measurements and all, which that time was done at KR Delhi, but now our own setup is up to 40 gigahertz at VNIT we can do. So you can see we could touch up to frequencies of 12 gigahertz and all in scaling up, and got this particular encouraging pattern. Now, basically, you will find that it's common sense. Now, if this is the pattern, and if I design it in one's complement fashion, so if the first one is the particularly some band or pass band, then the second design will be stop band that can get achieved and all. So that is what we are basically doing. So here you will find that it is exactly in reverse fashion, and again the design surface is there, the measurements were done and all, and the required functionality was achieved. Okay. Now, in this case, for millimeter or this thing, already Dr. Gaurav Chaitanya might have given you the session. He happens to be my PhD student only, and a third generation, because his guide or my co-guide Paritosh Peshwe happens to be my PhD student. So he happens to be student of my PhD student in a way. So here for these frequency ranges, we tried to explore the 3D printed technology also for various parameters to be achieved at these frequency ranges. So quickly I will get the results explored here. I don't know whether in his session he has covered this or not, but first of all, in 3D printed technology, it gives us lot of reconfigurability, plug and play mechanism, and secondly bending thing also, and conformal arrays also of the reflecting surfaces for various applications and all. So here you could see this is in plastic, the 3D printed dual band absorber was designed particularly, and for various angle of incidences, its performance for dual band, this thing was tested. Now here you can see the bending angle. If it's in first picture, we can see 5, 0, then 90 degree, then almost 135 and 180, like that it is there, means almost you can make a cylinder out of it. This kind of flexibility typically given by the material, where instead of giving for photolithography and other costly techniques and all, we have tried to model it with the 3D printing technology and all. So for this, now with various fractal cells, if they are to be explored and all, we tried various designs, the square, the pentagon, and this and that, and different types of geometries were tried. They were fabricated, measured, and all, and many of measurements were done in collaboration with IIT Indore. Now again, as I have said, that simple ideas basically influence your everyday life designs and all. Here you can see the Lego block his child was playing from, that this idea was picked up, that in fractal geometries, if we can have different topologies together and have a common substrate for it, then we can have different topology fixation and can get various frequency bands. So you can see the blue substrate is common, but sometimes it has a plus sign, or the square, or the higher plus sign, longer this thing, or swastik, and all different patterns together we are making and testing it and measuring it and all, and getting all desired performances with different angle of incidences and all. So this is how I just wanted to show you that at millimeter wave also some promising technologies are coming which you can try and can formulate particularly these designs. Some challenges would come with different ideas, you can counter them and all, like that it is there. Now once we deal with millimeter this thing and all, there is one very good paper in IEEE Access by Nayan Sarkar and all these people basically, and which is typically on the topic of applications of machine learning and deep learning in antenna design optimization. Now it's a review paper basically, it's a very long paper and all, but I will just give you the gist and all, because all these results are directly applicable to millimeter wave technologies and all. So what is neural network and how in reinforcement it works and all, and in antenna how it can be used, those details I will just skip here. Some tables are there, you go through this particular research paper, you will get, and then you will realize that the HFSS, I3D, CAD, FICO, or CST, all what you are using are basically working with these techniques and all. So how basically in antennas or components which are in millimeter wave, this thing, these kind of techniques can be used. Overall, what I can say, that if millimeter this thing comes and all, there would be lot of scope for optimization or decision prediction, precision, and all, like that it is and in all such cases you will find that you can use AI. AI will be basically used for optimization, adaptive beamforming and all, or if it is RF integrated circuit development, then precise placement decision and all, then design simulation, microwave component also. All these tools which are designed are based on AI basically. Circuit routing, layout design, modeling and predicting mutual coupling, assessment of beamforming robustness or accessing antennas and all. Sorry, assessing antennas and all, then antenna diagnostics, array calibration, basically what distance, what pitch they can work. Then if you want to go for generating beam generating networks and all in multiple this thing, then you will have to use AI. Then modeling, scattering, object detection, classification and all. Typically when millimeter wave technologies are used for imaging and also it will be used for radar, so you have to catch the enemy plane and plot it here and all. For that, this AI would be again required for RF imaging or imaging or biomedical applications and all. And finally, body area networks. These are the various domains. If you include millimeter wave communication frequencies here, at once the day will come that only antenna and CAD, FICO and CST won't help, but you will also need lot of signal processing in its support, and that you can't do without AI ML. And also what I will suggest finally is, please learn to know something about everything, and then finally try to integrate it for the millimeter wave combination and all. Then only in a focused way for the identified applications you will be in a position to work on these components, and you will be able to overcome the challenges which you will be facing and all. So I thank the SVS College and all for giving me the opportunity to present my thoughts. I hope that I have done my full this thing effort, and it might get justified basically, and some of the things which you can pick up. And as I have said, my contact credentials are available with the coordinators, or they are on the website also and all. So you people are always welcome for any kind of collaborative this thing and all. If any, I know that I have consumed the entire time and we have already reached to the end of the session. So if typically some short questions or these are there, then I can answer. Thank you.
Yeah, during this session, some of our participants, they have raised their hands. So now I request them, if they want to ask any question, they can. Yeah, Abhijit Jamdade, sir. Sandeep Pawar, sir.
Good evening, Ashwini sir. Ashwin sir.
Yeah, good evening. Yeah.
Sir. Actually, my domain is in that RF and antenna. I'm working in that domain.
Okay.
So right now, when anyone is working want to do the work in IRS, intelligent reflecting surface. So there, for the beam forming and other technology, the channel estimation and power estimation, signal strength calculation is required.
Correct.
So I don't know how to, because the channel estimation and the power estimation is somehow is related with the wireless network. A lot of equations
Communication.
and communication, lot of equations and other
Correct.
mathematical
Correct.
formulas are there. And
Correct.
when I am working in the antenna domain, so it is just related with too much with HFSS and other thing where too much equations are not there.
Yeah,
So
yeah.
there I am
No,
finding the
there also the
difficulties.
equations would come, but I know exactly what you want to ask. Now, see,
Ji,
you
ji.
are typically, you are in a
Designing
trapped
mode.
in
I
a
am the
situation.
designing. Huh,
No, no, but
huh, huh,
you are trapped in a situation. You will design, but your
huh.
design won't get validated unless it is tested in field. And when it
Ji,
comes
ji.
to field testing or the actual measurements and all, then all these things would come in picture. Now, there are
Yes,
two
sir.
ways
Yes,
of
sir.
doing it. One
Yes, sir.
is either you collaborate with one researcher who is good enough in communication. This you will have to
Mhm.
do. Because now at this juncture, if you try to be a master of communication concept and all, it will consume lot of time. Okay.
Okay.
And secondly, but still in your literature review, you involve components like which are related to channel estimation or communication parameter and aspects and all. And then
Mhm.
what you do is you make some IEEE transaction or standard papers and all as your reference literature or benchmarking literature. And
Mhm.
if the frequency range or the application identified is of similar kind, what has been shown in the paper and all, then you directly use their communication related results as it is in your this thing, and you can claim that this I have taken from the literature, I have worked on the design aspects only. Okay.
Okay. Okay.
So yeah, and second thing is you will have to be very good in tools like MATLAB. Okay, for this purpose, where MATLAB also has its own antenna box and all. There would be interportability required, where once the design of your antenna is ready, you with those characteristics will make it as a black box, and that black box has to be imported as a node into MATLAB, and then connect it with channel, characterize and all, put those parameters and then test your antenna. This is what actually you have to do. Okay.
Okay.
So, so then you won't get bothered about actual hypotheses and assumption and equations and all and things like that. But you will have to collaborate with one person who is there. Now, fortunately, in our department, if you want, there is Dr. Prabhat Sharma, who is a man of communication and has recently started in field of IRS. Also, he got a project from MIT, and recently he has come out with a working prototype which can be field tested, which was demonstrated at the Indian Mobile Congress also.
Oh,
So
super, super.
so you can seek his guidance, and very soon we are going to have a conclave also, where we will be having academic networking opportunity, and people working in IRS will be called for all these things and all, so
Oh,
they
so it
can
will be great.
participate. Yeah. So I will just suggest that you just keep on watching our department website and all, or just be in touch on LinkedIn with either me or this thing, and after every few days keep on messaging me, or you check our all posts and all. It can happen like then you can come to know when that event is. Generally, it will be during March,
March. Okay. Okay, sir.
month of March.
Thank you, sir. Thank you. Thank you.
Yeah, thank you.
Sir, there is one question in the chat box from Freda madam. She is asking, will pin diode become lossy at millimeter wave?
Yes, that is a question actually which everyone asks and all, but Now even recently, like I don't know, she has attended MapCon or so. There are improved versions also have come, which are very high performance and all, but then cost will be another issue. This is the case. But right now, whenever these active components for switching and all would be required, you don't have any other good alternatives to go for it and all. Okay, so the new designs have compensated for the losses. But yes, it will be there. That problem will always be there. If you see in the slide, I already mentioned that if you go for millimeter wave communication, losses would be the first thing which you will be facing in any way, or either these or other way.
Snehal madam is asking if any study material for further study can be shared.
Actually, all the things which I have shown are patented one, and these kind of things are there, and most of them are my research papers which are very much available as a open literature in IEEE Explore or other places and all. So you can definitely go, just type my name or all the names which were there, and you will get all the details there, all design this thing. And on Shodh Ganga, all the theses have been uploaded already.
Sir, one question from my side. What is the concept of 5G millimeter wave and what is its impact on wireless communication?
No, see, again, I am saying impact and all, nothing. Just thing is, all wireless basic concept. Just now, this gentleman asked that when it comes to channel, this thing and all, what is going to happen is concept of channel, interference, mitigation, these are not going to change. Okay?
Hmm.
Now, when you talk about 5G, in general, people will talk about the designated frequency ranges and all. But when you talk about 5G millimeter wave moment, you say your basic minimum standard starts from 24 gigahertz itself. Now you have fixed there suddenly. Whereas right now also, if you see even 5G, general 5G, not millimeter, I am talking, still the applications are limited only up to 6 to 8 gigahertz only, or even 5 gigahertz. Okay, all latest applications and all. So suddenly, like if you are changing your domain, typically because of the advantages at that frequency ranges, what you get and all, and your cell size, and then you can increase number of users and all. So many things are there, but this is all at the cost of increased complexity or things like that, because suddenly you are shifting from 5-6 gigahertz to 24 gigahertz and above, and then you will start talking about even 120 gigahertz or 1 terahertz or this and that frequency ranges also. Okay, when it comes to that, again I am saying is the advantages are at the cost of something. Okay, and that something means always you will find that you won't get test setups, the tools, fabrication facilities, these would be the problem. Okay, and secondly, your design complexity will also be of higher order as the wavelength is reducing and all. If you talk about feeding mechanism, now what will happen? You will find that at many places for devices there won't be any other alternative than waveguides and all, and actual this thing, and your regular components won't work there at such high frequencies. So again, integration comes in picture. So it will, all these challenges would be there, which you will have to face them.
Okay.
Now someone put a question which was like on my initial content that give information about online courses. So I don't know which online courses she is referring about. There are two MTech degrees which are online, and its information is very much available in the admission tab of the VNIT website itself. If you go there, everything you will get all details there. Those programs are run in partnership with EdTech called as IntelliPat. So if you just keep VNIT, IntelliPat, MTech, this thing, all details again will be there. Okay, probably I don't know, something is posted in chat box recently. Okay. Now there is one question from Devidas Chikle. Apart from antenna, what are other components to reach signal at the receiver with very low loss? Now
Loss.
in this case, you will find that other components means now whatever come in line, what is your application, whether you are designing a radar, RCS reduction, or you are designing an imaging gadget or whatever it is there. So the general block schematic which you draw, as a sensing this thing. The first part would be antenna array or FSS and all. Further, whatever will come, we'll have to deal with that low power signal only. But the main challenge will be with antenna or FSS only at the first take itself, because at millimeter wave, your angle of incidence matter, your orientation matters, whether it is a conformal array, then bending analysis, whether done or not, which material you have used, like that. There are n number of things which will come in picture. So basically you will find that. And then the further components, when I have said, as I have already given the list and all, so D plane, this thing, then variable load and all. So whether you are using a low noise amplifier, filters, band filters and all, whatever you, they all will have to deal with in first or second stages for these particular things. It will be there. Okay, so that is what I am saying, that actually when people say that I am working in millimeter, means it's a huge thing. Out of that also, in which one particular component compartment they are working, it depends on that. So I have shown you, application, they require signal processing, they require optimization, they require RF circuitry design which could support that processing and all. Without that, if you just design one dead dumb patch antenna which has not been connected to any of the system, and its radiation pattern is not measured or tested, then it carries no meaning. That you keep in mind. That's why my simple message would be, even that's why I have shown one slide, that you will have to learn basics of AI/ML also as it progresses further, because you may have to write your own tensor equations, or you will have to solve your own structural analysis, or use some computational electromagnetism method for optimization and all. If that is to be done, one thing gives rise to another problem, and then you have to find a solution. This goes on. Today, in stipulated period of time, my job was to give a picture. Now you choose where you want to work, in accurate or acute component designs, or backend, or process, or channel of IRS and signal processing of IRS, like that it is there.
Hello, sir. This is Dr. Ranjan Bala Jain.
Yeah.
Excellent session, and so many case studies you have presented and gave research direction. Now, one question is there, that is related to cognitive radio. The
Huh?
question is, you have used spectrum sensing algorithm, energy detection, cyclostationary detector, and many more. And
Mhm.
out of that, it is observed that energy detector is the most efficient one, right? So my
Hmm.
question here is that whether you are using this energy detection using software, signal processing, or you are having hardware for energy detection.
No, no. We actually had a hardware which can get reconfigured with our algorithm entered into that.
Means we are having antenna is capturing the signal in different
Correct,
different frequency
correct,
region.
correct.
Now
But
after
then
that we have to
detection in,
detect whether this is present or absent. For
correct.
that we will require hardware, or we are using, so means you are using software. That's my
No, no,
question.
no. That is what I'm saying. Hardware, software, co-designed, complete reconfigurable system. That PXI chassis gives you a reconfigurable hardware to which you connect your antenna, and through LabVIEW, you can control it and write the entire algorithm and get loaded, like loading an FPGA. This
Okay, okay,
you
okay,
can reconfigure it and program it. Sorry, program it basically, so that that antenna can do scanning and all, and
okay,
it will sense and give back the result also. So
okay.
that's why these devices are quite costly. That PXI NI chassis, it costed us at that time something around 76 lakhs or something like that.
Yes, yes.
This I'm
Thank,
talking 2014-15. That time means now it will cost around 1 crore plus or whatever.
hmm. Okay, sir. Thank you, sir.
So
Thank you.
I will tell you the cheap options of that. Don't go after NI and all. I hope none of their employees attending the session. You can go for this thing, GNU radio and all, which are open source and compliant hardware. You will get at very cheap rate and small
Yes,
kit.
sir. Yes,
That
sir. We are
don't you
looking
prefer?
through the. We are
Yeah.
looking that. Okay. Thank you. Thank you, sir.
Yeah, now I request participants to please turn on their cameras for a moment so that we can take a photograph.
Sir, I request you to stop sharing your screen, please.
Yeah. Sorry, I forgot it.
I hope everybody is ready. I'm taking the picture.
The organizers themselves are not visible. Coordinators
Sir,
and
I
all.
am there. I am there.
Ranjan madam. Yeah.
हाँ, अच्छा उनके दो ये दिख रहे हैं इसलिए समझ
Yes, I am connected with two devices.
Yeah, thank you, everybody. It is done.
Okay. Thank you, sir, for that insightful presentation and very excellent coverage and interactive session. I'm sure that we'll all have better understanding of millimeter wave antenna design concepts, the challenges, and their applications. Thank you so much on behalf of FDP team, Department of Electronics and Telecommunication Engineering of VESIT, and all the participants. Thank you, sir.
Yeah, so I also thank team of Visit and all the participants who have given a patient ear to or have uh, attended the my session. And I have made some humble effort to present few things or share my experience, whatever I have achieved so far. So you are welcome for any kind of collaborations and all. And with your this thing formal announcement of concluding of the session, I will also end the meeting. Okay, thank you. So I
Thank
or
you, sir.
yeah,
Thank you, sir.
I leave I
Thank you.
will leave the meet. Thank you.
Now I request Jyoti Davkar madam to please take the next session ahead.
Yes,
Over
yes,
to you, madam.
yes, sir.
Hello.
Thank you.
Jyoti ma'am, sir is there. Dr. Sreenath Reddy is there.
Yes,
Welcome, sir. Welcome, sir.
Hello, madam.
Hello.
Is my voice clear?
Yes,
yes,
sir.
sir.
Thanks.
Yes. So moving on. Good evening, everyone. Now I am your host, Mrs. Jyoti Bagate, Assistant Professor at the Electronics and Telecommunication Department in BS Technology. Today's second session is on reconfigurable intelligence surfaces and MIMO, and that will be delivered by our guest, Dr. Sreenath Reddy. I take opportunity to introduce him on this platform. Dr. Sreenath Reddy received master's and PhD degree in RF and microwave engineering from the Indian Institute of Technology, Dhanbad, India in 2016 and 2021 respectively. He received Raman Charpak Fellowship in 2019-20 and carried out part of his PhD work at Sorbonne University, Paris, France for the 6 months from 2021 to 2022. From Feb 2022, he has been working as an assistant professor at Department of Electronics and Communication Engineering at Indian Institute of Information Design and Manufacturing, Kancheepuram. Dr. Srinath received the Young Scientist Award 2 times in DAS 2021 at Rome, Italy, and at Atlantic Radio Science Conferences in 2024 at Gran Canaria, Spain. He is currently executing his research project of more than 1 crore and funded by DST, DRDO, and IIITDM. He is also founding advisor of IEEE Joint Antenna and Propagation Society and Microwave Theory and Technology Society Student Branch Chapter at IIITDM Kancheepuram. I welcome Sir and request him to take over the session. Over to you, Sir.
Thank you so much for the introduction. Let me share my laptop screen. I hope my laptop screen is visible and slides are changing as well. Can you please confirm?
Yes, sir. Yes. Yes.
Yes, yes, visible.
Okay. Good evening to all the participants. My name is Dr. Sreenath Reddy. I am currently working as an assistant professor at IIITDM Kancheepuram. Before going into the technical talk, first I would like to thank the organizers, especially Dr. Ranjan Bala, for contacting me and asking me for a resource person in this Atal FTP program. So as a part of this program, I'm going to deliver a talk on reconfigurable intelligent surfaces and MIMO, which are considered as the key technologies for millimeter wave frequencies. I've divided the presentation outline into 3 parts. In part 1, introduction, there I will show the differences between the sub 6 GHz and millimeter wave frequencies. And in part 2, the MIMO technology, and in part 3, reconfigurable intelligent surface. So first, let's see what are the benefits we will get when we use sub 6 GHz frequencies over millimeter wave frequencies. Nowadays, when we talk about 5G, we are talking about sub 6 GHz frequencies, that is less than 6 GHz frequencies, as well as millimeter wave frequencies. So millimeter wave frequency basically starts from 24 GHz. So in this slide, I'm showing the benefits of using sub 6 GHz frequencies over millimeter wave frequencies. Whatever the frequencies we have used until 4G wireless communication, those are sub 6 GHz frequencies. So for sub 6 GHz 5G, we don't, it doesn't require anything more than tower upgrades because of the same frequency. But when we move to millimeter wave frequency, so obviously we need more tower upgrades, which involves cost and complexity. And the lower frequencies obviously travel longer distances. This statement is valid with the help of this equation. This is a free space path loss equation. LP is the free space path loss. F is the frequency between the transmitter and receiver. F is the frequency, and D is the distance between transmitter and receiver. So if we keep D same, you can see LP is directly proportional to F. So the higher frequencies undergo higher path losses. And not only that, you can see here millimeter wave frequencies can be easily attenuated by trees, buildings, rain, even fog can attenuate the millimeter wave frequencies. So the disadvantage of millimeter waves is obviously the benefit of sub 6 GHz waves. For an example, the 30 GHz signal is undergoing 23 dB more path loss as compared to the 2 GHz signal. In sparsely populated rural areas, there is no meaning in implementing high-cost millimeter wave 5G because as these frequencies travel shorter distances. If I talk about millimeter wave frequency application, you can find it the concerts or in stadiums where the network congestion is very high. For example, Verizon, a famous telecom company in USA, has developed the millimeter wave 5G, and it tested the millimeter wave 5G in a football event, and it becomes successful. So the lower frequencies, that means sub 6 GHz 5G, is useful where network congestion is low. Example is rural areas. Whereas millimeter wave 5G, where the network congestion is high, like in urban areas or sporting events, etc. Here I'm showing the benefits of millimeter wave frequencies over sub 6 GHz. Obviously, the millimeter wave spectrum is the new frequency territory because until 4G, that means 1G to 4G, we have used only less than 6 GHz frequencies. Now with 5G, we entered into the millimeter wave spectrum, so obviously it's a new territory. And you will find very less applications here as compared to the sub 6 GHz frequencies. Since you have less frequencies, obviously you have larger bandwidths. So bandwidth is directly proportional to data rate. That's why the millimeter wave frequencies can offer you the higher data rates. Here you can see the millimeter wave 5G offer 10 times higher data rates with a peak data rate of 10 Gbps as compared to sub 6 GHz 5G. Another benefit is as frequency increases, obviously antenna size will be reduced. So within the same size, you can keep more number of antenna elements, which obviously give higher gains in the desired direction, which we call it as phased arrays. The millimeter wave 5G is more useful in places where network congestion is high, like as I discussed in the last slide. They are especially useful in sporting events, airports, concerts, etc. And many telecom companies have in airports or sporting events, and millimeter wave 5G has become a highly successful one.
Hello, Dr. Reddy. Your screen is not visible.
Screen is visible, but
Actually,
not
screen is
audible.
visible.
Sir is not
audible.
I mean, yes, presentation is not audible. A presentation is not seen, sir.
Your
Sorry.
screen is also not visible to you.
Sir, yes. Hello, sir. You are not audible also. Okay, let me talk to him. Hello, sir. You are not audible. Sir is joining in sometime.
Am I audible now? Hello?
Yes, sir.
Yes, sir.
I'm sorry for the interruption.
It's okay, sir.
So I hope the laptop screen is visible now.
Yes, sir.
I don't know up to what slide I have talked about. Okay, let's start from here. So there are several technologies at millimeter wave frequencies, like massive MIMO, phased arrays, RIS, small cell technology. Whereas at lower frequencies, like sub-6 GHz frequencies, we have a technologies like MIMO, cognitive radio, full duplex, etc. But I'm going to cover only two technologies in this talk. One is MIMO and another one is RIS. MIMO is not only useful for lower frequencies, but it's also useful for higher frequencies, that is at millimeter wave frequencies, in the form of massive MIMO. Just a second. Okay. MIMO started its trials from fourth generation wireless communication, and it become a lot successful, and it find lots of applications as well. One practical application I am showing here, the left side one is a router with a single antenna. It's a TP-Link router, and the right side one is also a router with two antennas. The left side one is having the peak data rates of 150 Mbps, and the right side one is having 300 Mbps. So the data rates has been doubled by placing two antennas. So the concept behind this is MIMO technology. So at the end of this MIMO basics, you will understand how placing two antennas is increasing the or doubling the data rates from 150 Mbps to 300 Mbps. So MIMO technology comes under antenna diversity scheme. Uh, we already know what is diversity. So diversity techniques can supply to the receiver several replicas of the same information over independent fading channels. We have time diversity, frequency diversity. For example, if I take frequency diversity, a signal will be sent at frequency f1 and also at other frequencies if the signal at frequency f1 undergoing large fading and unable to reach the receiver. We expect that at other frequencies the fading will be very low and the signal will be delivered to the receiver, thereby improving the reliability of communication. That's what diversity schemes are. So, but time and frequency are very important resources that we should not waste. That's why the researchers have explored the antenna diversity scheme. In antenna diversity, we have two more. One is spatial diversity, another one is polarization diversity. In spatial diversity, you have multiple antennas. For example, if I talk about SIMO, single input, multiple output, you have one antenna at the input side and multiple antennas at the output side. MISO means multiple input, single output. MIMO is multiple input, multiple output. Whereas in polarization diversity, you have a single antenna and it acts in two modes. For example, in horizontal mode and vertical mode. The signal sending through horizontal polarization mode will have zero correlation with the signal sending through vertical polarization mode. So different fadings, that means independent fadings, you have a diversity. So antenna diversity scheme explores the space diversity. And one more benefit of this diversity scheme is the data rates also will be increased. So what is the benefit of increasing, the channel capacity also will be increased. The benefit of increasing the channel capacity is this equation has to be maintained every time for error-free communication. If diversity scheme improves the channel capacity, so it is giving you the scope to increase the data rate by moving to high-end digital modulation technique, and you can still maintain this equation. So two benefits of diversity scheme: one is improving the reliability, another one is improving the channel capacity. First, let's see the size of communication. You have a single antenna at the transmitter side and single antenna at the receiver side. And I have considered a multi-path propagation scenario. So obviously you have a large number of paths, but here I'm taking only 3 paths for simple explanation. The output signal, the received signal at receiver is equal to transmitted signal into path 1 plus path 2 plus path 3. So there might be a chance that all these 3 paths will undergo destructive interference at the receiver location and you don't get any signal at the receiver. So there will be error in communication. So this is one disadvantage, the biggest one. Let's see the other disadvantage. Here the channel capacity is written in the equation here. PT is the transmitted power, sigma square is the noise power. So PT by sigma square is SNR ratio and mod H square is the channel. So this is the channel capacity formula for the size of communication. And the problem here is there will be error in communication if all these 3 paths will undergo destructive interference. Now let's see how we can solve this disadvantage by placing one more antenna at the receiver side. So here instead of single antenna, 2 antennas are placed now. So at antenna 1, the received signal will be transmitted signal into path 1 plus path 2. At antenna 2, the received signal will be transmitted signal into path 1 into delta phi 1, because the path 1 signal is undergoing extra phase difference of delta phi 1, and path 2 into delta phi 2. So there might be a scope that path 1 and path 2 are undergoing destructive interference, so you don't receive any signal at antenna 1. But definitely you will receive a signal at antenna 2 because now you have the extra phase differences. So there will be thereby enhancing the reliability in communication by placing two antennas at the receiver side. The other benefit you will get by using multiple antennas at the receiver side is improvement in the channel capacity. So in the last slide, you have seen only mod h square term. Now you can see here mod h11 square plus mod h21 square. And these two are positive terms, and definitely there will be increase in the channel capacity. So once again, increasing in the channel capacity gives us the scope to increase the data rates by moving to high-end digital modulation techniques. Similarly, if you place multiple antennas at the transmitter side, you will get the same benefits, and we call it as MISO technology, multiple input, single output. And if you have multiple antennas at both transmitter and receiver, you have a MIMO technology. So these are the channel capacity formulas for SISO, SIMO, MISO, and MIMO. But whatever I have discussed until now with respect to MIMO technology is only the spatial diversity mode. MIMO can act in two modes. One is spatial diversity and another one is spatial multiplexing. Let's see what are the differences between them in this slide. So the left side figure is a spatial diversity mode, MIMO acting in spatial diversity mode. And the right side figure is a MIMO acting in spatial multiplexing mode. So in spatial diversity mode, we are going to send the same signal through multiple antennas. For example, let's say 101 is the data that we need to send. Obviously, it will go through some digital modulation techniques, but I'm not showing here for easy explanation. And you can see the same data 101 is sending through three different antennas. So the concept behind this is if an antenna is not able to deliver the signal, deliver this message to the receiver, the other two antennas may deliver, because the signals sending through different antennas will undergo different fadings. So there will be reliability improvement will be there when MIMO acts in spatial diversity mode. In spatial multiplexing mode, first the data will be divided, like the first bit is going through the first antenna, second through the second, and third through the third. So let's say each bit is taking 1 second. So within 1 second, one bit can be sent. So for sending 3 bits, you will need 3 seconds. But with the concept of MIMO technology, within 1 second, now you are sending 3 bits. So thereby the increasing the data rates to 3 times by using the 3 antennas at the transmitter side. So the MIMO in spatial diversity mode improves the reliability, and MIMO in spatial multiplexing mode improves the data rates. If you use 2 antennas, ideally the data rates will be doubled. If you use 3 antennas, the data rates will be tripled. Let's see the practical scenario. First, I am taking the bits, 8 bits I am taking as a data. So now I'm considering a QPSK modulator where the 2 bits will be combined and form one symbol. So you have 4 symbols, finally 1, 2, 3, 4, with a phase difference of 90 degrees. And all these 9 symbols will be sent through a channel. Let's assume the channel is having 100 megahertz bandwidth. And this channel, you can see the y-axis, I mean the vertical axis. This is a frequency and the horizontal axis is a time. So the frequency is having 100 megahertz bandwidth, and it is divided into 10 subchannels like 0 to 10, 10 to 20, 20 to 30, etc. So in 0.1 microsecond, how many symbols this channel can send? Total 10 symbols, because you have 10 subchannels. Because 10 subchannels are there, you can send 10 symbols in 0.1 microsecond. Let's see how MIMO increases the data rates here in this particular scenario. So when we introduce the 2x2 MIMO here, the 2 and 4 are going through the same slot. But here if you see, the 2 and 4 are in different slots with respect to the vertical axis. But here the 2 and 4 are going through the same slot. That means 2 and 4 are not divided in time, not divided in frequency. They are divided in spatial domain. That's what spatial diversity is. That's what antenna diversity is. Now, in 0.1 microsecond, in this particular scenario, you can send 20 symbols. In the last case, you can send only 10 symbols. So the data rates has been doubled by using 2x2 MIMO. So that's why, coming back to the original question, when where I showed the router, there using two antennas has double the data rates from 150 Mbps to 300 Mbps. The reason is their MIMO acts in spatial multiplexing. So let's see what will happen to MIMO technology in the absence of multipath, where there is no multipath scenario between transmitter and receiver. Practically, it's not possible. This kind of scenario possible in anechoic chamber, which is used for testing antennas or any microwave structures, or to analyze the far field performance of microwave structures like FSS, absorbers, etc. Basically, anechoic chamber is a room whose walls are coated with the pyramidal absorbers. These are pyramidal absorbers. When a signal hits the pyramidal absorber, there will be no reflection. If there are no reflections, obviously there will be no multipath scenario. Only line of sight communication will be there between the transmitter and receiver. Now, if I want to use a MIMO concept here, I need to place one more antenna here. Let's assume two antennas are placed at the transmitter side. Even if second antenna is placed at the transmitter side, it also has the same line of sight communication with the receiver. So the path 1 and the path 2 with the second antenna will be same. I mean, the line of sight communication. If both the paths are same, there is no exploring of spatial diversity. If both the paths will undergo the same feeding, there are no independent feeding channels. So the MIMO technology loses its performance in the absence of multipath. But the advantage you will get is when you use one more antenna, these two antennas will combiningly act like array antenna, and it will give you the array gain. So the array gain is visible. For example, if I take MISO, multiple input single output, here NT is nothing but array gain, and here rho R is nothing but signal to noise ratio, and C is the channel capacity. Similarly, in case of MIMO, you have NT into NR, number of antennas at the transmitter side and number of antennas at the receiver side. So in the absence of multipath, MIMO loses its concept, MIMO loses its performance, no spatial diversity, no spatial multiplexing, but it acts like an array antenna and it will give you array gain. So if someone is working on MIMO, or if he wants to work in MIMO technology in the future, for them I'm showing the rough idea of the design methodology of MIMO antennas. First, depending on the application, you have to choose the frequency range, how many number of antenna elements you have to use. In 2x2 MIMO, you have to use 2 antenna elements, 4x4, 4 antenna elements, etc. And what is the operational bandwidth and how much isolation you need between the antennas, and what about ECC, envelope correlation coefficient, what are the diversity gain, what are the multiplexing gain. First, you have to decide all these parameters. Then start the design with the single antenna element, and then by choosing the appropriate substrate and optimize the design to achieve the required bandwidth. Then replicate that single antenna to multiple antennas. If you want to design 4x4 MIMO, you have to replicate 4 times. And place all those 4 antennas on the same substrate. So if you place all 4 antennas on the same substrate, obviously some mutual coupling problem will be there. That means you need to enhance the isolation between those antennas. So there are lots of isolation techniques available in the literature. Out of them, first try with the antenna rotation based isolation technique. In the coming slides, I will show you what is that antenna rotation based isolation technique. First try this technique because it does not involve any extra circuitry, so thereby no extra losses. If it does not work, then go to the other techniques. And I'm showing the other techniques in the coming slides. And if possible, respect the 0.5 lambda distance between the antenna elements. If you respect this distance, 0.5 lambda, so obviously you will get a good MIMO performance. I mean, good ECC values you will get, good multiplexing gain values you will get. Finally, optimize the design to achieve the required parameters. Obviously, when you place more number of antenna elements on the same substrate to have a MIMO concept, obviously the disadvantage is between the antennas, between the multiple antennas, you have a mutual coupling problem. So reducing the mutual coupling is nothing but increasing the isolation between the antennas. So we have so many techniques available in the literature. These are some of the techniques. I'm going to show you one by one. The first one is a decoupling network based isolation. Here I'm taking 2 ports and 2 antennas, that means 2x2 MIMO. So between the 2 antennas, you need to place some decoupling network. For example, you can, if you want isolation at 2.4 GHz, you can put a band stop filter at 2.4 GHz. And that band stop filter is nothing but decoupling network. But when you place a band stop filter between the 2 antennas, the S11 parameter, that means the impedance parameter also will change. And to bring back the S11 to the original value, you have to use some matching network. And this matching network is in the form of stubs, balloon, etc. The second one, the defected ground structure. You can see this is a figure without defected ground structure. And this is a monopole antenna where slots are placed in the ground and these slots will radiate. But these two monopoles are placed very close to each other. So obviously the mutual coupling problem will be there. And to stop the mutual coupling, a T-shaped structure has been placed, that means has been cut from the ground plane, and it is located in between the 2 antennas. And this T-shaped structure acts like a resonator, and it stops the frequency where you want low mutual coupling. And it's not compulsory that you have to use T-shape. There are lots of shapes available in the literature like slits, dumbbell, or some random geometry. The other one is the parasitic elements and neutralization lines. They follow the same concept, except the fact that neutralization lines are in direct contact with the antenna part, but parasitic elements are placed in free space. This figure shows the parasitic element based technique. This is one antenna, this is one more antenna where the fields are in the upward direction, and those fields are also responsible for mutual coupling because they are in the same direction. And to cancel out those fields, you have to place a parasitic elements with the opposite fields. These opposite fields will get cancelled out with the mutual coupling fields, and it increases the isolation. And neutralization lines also will have the same concept, but they are in direct contact with the antenna elements. And next one is the metamaterials. Metamaterials are artificial structures, and they have band gap in their frequency band. And you have to explore that band gap nature in order to increase the isolation. And this is one metamaterial which is of SRR shaped. This is one more, this is one more. So total 3 SRR elements, which combiningly called as metamaterial, is placed between the 2 antennas. And the band stop frequency of this metamaterial is same as the frequency where you need low mutual coupling. If you want at 2.4 GHz, you optimize this design for 2.4 GHz. You will get a good isolation between the antennas. And the last one is the antenna placement and orientation. Here, actually this figure combines 2 techniques. First, let's assume that there is no this plus symbol. First, let's talk about this figure without plus symbol. So we have 4 antennas, first, second, third, and fourth, and all these 4 antennas are placed orthogonal when compared to the adjacent antennas. The reason behind placing orthogonal manner is, you can see in the first antenna, the current direction is in this way, in the upward direction. Whereas for the second antenna, it's in the horizontal direction. So you have 90-degree difference. So thereby there is a chance that you will get low mutual coupling. because of 90-degree difference. The same here. The first and fourth antenna are 90 degrees apart from each other. I mean, their currents are 90-degree apart. So thereby you have a chance of low mutual coupling. But the problem with this technique is it always won't work. You have sometimes you have to use the combination of other techniques as well. For example, in this figure, the slits are placed in the ground plane. This slit is nothing but this plus symbol is nothing but a defected ground structure. So this particular figure uses two techniques. One is antenna rotation, another one is defected ground structure. Whereas coming to antenna placement, I'm not talking about antenna orientation, only antenna placement. Antenna placement is nothing but you have to place two antennas very far from each other. If you do that, obviously the current generating from one antenna will never reach the other antenna because they are very far from each other. So thereby you will get good isolation. But the problem in that technique is in mobile terminals, like in mobile phones, you don't have that much space to keep the distance very large between the two antenna elements. So obviously this technique won't work at mobile phones or any small devices. But the best technique we have is the antenna orientation. So summarizing the MIMO advantages and disadvantages, the advantages, MIMO increases the reliability when it acts in spatial diversity mode. It increases the data rates when acts in spatial multiplexing mode. In case of no multipath scenario, MIMO will provide only the array gain. And so since MIMO increases the array gain, it's more suitable for the beamforming operation, and beamforming is of utmost importance for 5G millimeter wave frequencies like 60 GHz. Coming to the disadvantage, MIMO obviously occupies a large space because if you put more number of antenna elements, the space also will be very large. And one more disadvantage is the biggest one. You always have to take care about the isolation and MIMO parameters like ECC, diversity gain, mutual coupling, etc. You always have to use some kind of isolation techniques. Now I'm moving to the second technology, that is reconfigurable intelligence surface. So I hope there is no problem with the network. My voice is clear, slides are moving, right? If there is any problem,
Yes,
please
sir. No issue.
thanks. So now moving to the other technology, the reconfigurable intelligence surface, where in which many researchers, not only from India but across the world, are doing research on it to bring the RIS from concept into reality. RIS is now just a concept, but and we already know there are some small scale experiments are going on RIS, but RIS is not deployed in real time till now, because there are lots of unanswered questions surrounding this concept. So I'll go through the basics of RIS, then I'll show you one algorithm how to design the RIS, and I'll show you what are the unanswered questions surrounding the RIS. So this is our current wireless network, where you have transmitter section, receiver section, and a fixed wireless environment. There is a fixed channel. We don't have any control over the channel. We can receive the feedback from the receiver. Based on that feedback, the receiver can be controlled. This is all about the current wireless network, which you already know. By incorporating the RIS in the channel, we can have a smart wireless network. In the smart wireless network, we not only receive the feedback from the receiver, but we also receive the feedback from the RIS. When we place the RIS inside the channel, and that RIS also will give one feedback, and based on this feedback, that RIS can be controlled. And if you control the RIS, you can control the channel. Controlling the channel is nothing but controlling the wireless environment. So you have a smart wireless network. So this is one figure showing how the RIS assisted cellular network model looks like. For example, you have a base station here. This let's assume this base station is communicating at millimeter wave frequencies. So this base station wants to send a signal to user terminal 1, 2, and 3. Definitely base station is in direct contact with the user terminal 3, so it can directly send a signal. It can also send a signal to user terminal 2, but it is unable to send a signal to user terminal 1 because there are a blocking buildings between the base station and user terminal 1. As I discussed before, millimeter wave frequencies can be easily attenuated. Even buildings, trees can attenuate the millimeter wave frequency, so they can't travel to user terminal 1. So user terminal 1 is not receiving any signal. So one way of solving this problem is to keep some kind of relays or extra base station somewhere here or here and send a signal to user terminal 1. But that increases the cost. The other alternative we have is the RIS concept. So instead of sending the signal to all user terminals from the base station, we are sending the main signal from the base station to RIS first. And now this RIS will take care of sending the signals to all the user terminals. You can see it's sending the signal to user terminal 1, 2, 3 as well. But it's not easy to design the RIS because it involves tunable elements like varactor diodes, and those varactor diodes will be controlled by extra circuitry called FPGA kit. Not only that, it has to give lots of beam manipulations. For example, you can see when a signal hits the RIS at 10 degrees, for example, let's say it's hitting at 10 degrees, you need reflection at 30 degrees or sometimes minus 60 degrees. So it has to give anomalous reflection. That means the reflection angle is not same as the incidence angle. Similarly, it has to give the transmission at a different angle. And when user terminal 1 moves from one location to another location, this beam also should shift their position, should shift that direction. So it's not easy to design such kind of structure, and researchers are trying very hard to do that. These are some of the objectives that RIS should achieve. The first one is the anomalous reflection. Incidence is happening at one angle, reflection is happening at a different angle. The same here. You can see incidence is happening at one angle, the reflection is happening at a different angle. Next, anomalous transmission. Beam splitting, power splitting. Power splitting is nothing but when we instant 100 watts of power, let's say 100 watts of power is instanting an RIS. Sometimes you need 50 watts to user terminal 2, 30 watts to user terminal 1, 20 watts to user terminal 3. So it has to do the power splitting as well. Then focusing, collimate. So these are some of the objectives that any structure should achieve in order to behave like an RIS. And it's not easy to achieve. And to design the RIS, the researchers tend to use meta surfaces or meta gratings. These meta surfaces or meta gratings are 2D versions of meta materials. Why? So a small introduction is also is already given to you about the meta materials. So basically, meta materials are artificial engineered structures. They are not naturally available materials. You have to manufacture them, and they will give unusual properties like negative permeability, negative permittivity, etc. So, and you have to use such kind of materials in order to design the RIS. You cannot use conventional materials. Let's see why we cannot use conventional materials. When we incident an angle, when a signal instant at a conventional angle, conventional material with an angle of theta in, it will reflect with theta out. And when we apply a Snell's law here, n1 sine theta 1 equal to n2 sine theta 2, and n1 n2 will be same because incidence and reflection are in the same medium. So you have theta out equal to theta in. The same with the transmission as well, because the conventional materials follows the Snell's law. So if you want to change theta out, you have to change theta in. But this is not what happening in case of practical scenario. This is theta in and this is theta out, and theta out will never be the same as theta in. So definitely the conventional materials you cannot use to design the RIS. So the alternatives we have is meta surface or meta gratings, which are 2D versions of meta materials. And this meta surface or meta grating consisting of a unit cell with meta atoms. And when you control those meta atoms, you can control this theta out. And these meta surfaces and meta gratings will never follow the Snell's law, because that's what the definitions say. They have unusual properties, and by controlling the meta atoms, you can control theta out, and you can achieve different kinds of beam manipulations. That's why the researchers have explored these two options for designing the arrays. So first, let's see about the meta surface one. It involves two levels. The meta surface design procedure has two levels. One is macroscopic, another one is microscopic. So in macroscopic, depending on the beam manipulation, first you have to define the electric and magnetic fields. For example, if I want to design a meta surface for anomalous reflection, first you have to define the fields. What are the fields here on the surface of the meta surface? Exactly on the surface. Once you define those fields, you put those fields in these two equations. These are generalized sheet transition conditions. Once you put here, you will get a z and y value. You can calculate either z or y. This is nothing but a surface impedance, and y is nothing but surface admittance. You calculate one of them, and then you go to the microscopic procedure. And this microscopic procedure is completely dependent on a commercial software like CST or HFSS. So you go to CST HFSS, you take some random unit cell and you try to optimize that unit cell, and you try to achieve the Z value. When you achieve this Z value, you can achieve this electric and magnetic fields. That means you are achieving the desired beam manipulation. But the problem here is in this particular example, which is shown for anomalous reflection, this is a meta surface and it consisting of 8 meta atoms per unit cell. The yellow colored ones is nothing but a unit cell. So this unit cell has total 8 meta atoms, 1, 2, 3, 4, 5, 6, 7, 8. Now you have to optimize all these 8 meta atoms simultaneously in order to achieve a anomalous reflection. So even with the commercial softwares like CST, HFSS, it's very difficult to optimize all 8 simultaneously. Here I'm talking only about a anomalous reflection. For example, if I need power splitting and advanced beam manipulation, there you need to use more than 8 meta atoms. So increasing the number of meta atoms obviously increases the optimization complexity, and you just simply can't rely on those softwares, because it will take 3-4 days, even 1 month to optimize those meta atoms. So we don't have any general procedure here to design a meta surface for a given beam manipulation. That's why the researchers are exploring the option of meta grating. So the concept of meta grating is when an electromagnetic wave hits the meta grating, currents will be induced on the meta atoms. So first let me show you the meta grating figure. This is a meta grating unit cell that my research lab have considered. The B1 is nothing but a bottom layer. Yeah, B is a bottom layer and C is a top layer, which are located on the substrate, having permittivity, relative permittivity epsilon R2, and H is height of the substrate. So total how many wires are there? 14 are there. So I1 to I14. So these are nothing but copper traces. So total 14 wires, I'm calling them as wires. So out of 14, only 6 are loaded with capacitive type meta atoms. This is a capacitive type meta atom. This is also one capacitive type meta atom. So total 6 meta atoms are there and 8 unloaded wires. So out of 14, 8 unloaded wires and 6 loaded wires. That means 6 meta atoms. Now when an electromagnetic wave or when a signal hits the meta grating, currents will be induced on these wires. So when currents induced, these meta atoms will get excited. When meta atoms excited, they act like secondary sources and they re-radiate the incident wave into infinite number of modes in both reflection as well as in transmission. Here M is the FB number, which is also called as Floquet-Bloch mode number. M is nothing but Floquet-Bloch number. And this M ranges from minus infinity to infinity. But you always don't need this M value from minus infinity to infinity. You have to limit the modes. That is possible by choosing the periodicity of the unit cell. So Ly is the periodicity of the unit cell. By choosing the Ly value, you can decide how many modes you want to allow. For example, here 6 modes are allowing, 3 in reflection and 3 in transmission. And now by controlling these modes, you can have different beam manipulations like power splitting, anomalous reflection, anomalous transmission, etc. This is the general procedure, general algorithm followed in the literature in order to develop a meta grading for any kind of beam manipulation. But the problem with this algorithm is it is used only for the static meta grading. It cannot be used for a reconfigurable meta grading. But our goal is to design a reconfigurable meta grading. The reconfigurable meta grading can only act like RIS, because a single structure should achieve a lots of beam manipulations. So to explain the proposed algorithm, this is the structure I have taken. Once again, the same structure. Total 8 unloaded wires and 6 loaded wires, and the meta atom is a capacitive type meta atom. One of the reason why I have taken a capacitive type meta atom is at the end I am going to replace this capacitive type meta atom with a varactor diode. Whatever the capacitance it will give, the same we can achieve using varactor diode. Thereby we have a chance to develop a reconfigurable meta grading. For example, if I use some kind of random geometry like SRR type or omega type or helix type, I cannot replace them with a varactor diode. So this is the main reason why I have taken capacitive type meta atoms. And why I have taken only 6? Because this algorithm, whatever I'm going to show you, it allows only 4 modes. As per the literature, if you want to control 4 modes, you need to have 4 meta atoms. But here I am taking 6 meta atoms. Once again, the reason is I want to design a reconfigurable meta grading, which not only achieve a single beam manipulation, but variety of beam manipulation with the same structure. So this is the so before going into the algorithm, first I'm explaining the notations here. Ly is the periodicity of unit cell. So here Ly is the periodicity of unit cell. And total 4 modes we are allowing, 2 in transmission and 2 in reflection. So those 4 modes are, you can see here, this is the incident wave. And this 20%, the black color one, this 20% is nothing but M equal to 0 mode in reflection, because this is reflecting. And this pink color one is nothing but M equal to -1 mode in reflection. So that corresponds to M equal to 0, R here is reflection, M equal to -1, R is reflection. So 20%, 20%, so 0.2, 0.2. And this mode, the red color one, this is a M equal to 0 mode in transmission. So M equal to 0 mode in transmission. Sorry, here the efficiencies are written wrongly. This is 0.2 and this is 0.4. And this is nothing but M equal to -1 mode in transmission. And these are the targets. These are the target efficiencies. And total 14 wires are there. So you need to have I1 to I14. So out of on the 14 wires, we have currents I1 to I14. And total we have 6 unloaded wires. 8 unloaded wires. Those are the impedances of unloaded wires. And these are the impedances of loaded wires. From the impedance, we can get capacitance. And from capacitance, we can get the width. So this is the algorithm. So it's very difficult to explain the algorithm in a few minutes. So what I'm going to show you is I'll run the MATLAB code which we have developed in the lab in order to make you understand what exactly the algorithm will give. So I hope you are able to see the MATLAB screen, right?
Yes,
So
sir. We
are you
can
able
see.
to see? Yeah. Yes. Thanks. So this is the algorithm with consisting of lots of functions. So when we run this, so first this algorithm will ask us that on what substrate you want to design a metagrading. For example, let's assume that I want to design on Rogers 5880. So for Rogers 5880, the relative permittivity is 2.2. Then it will ask us what is the height of the substrate. I am selecting a standard height which is available in the market, that is 1.575. Then it will ask what is the operating frequency in terms of 10 power 9. E power 9 is nothing but in terms of 10 power 9, that is gigahertz. So let's say 10 gigahertz. So 10 e power 9. 10 into 10 power 9, that is 10 gigahertz. So next it will ask what is the incident angle. So what is the incident angle means at what angle you are incidenting on a metagrading in terms of pi. So I'm selecting 10 degrees. 10 degrees is nothing but pi divided by 18. 180 divided by 18 is nothing but 10. Next it will ask us what is the outward angle. Outward angle is nothing but what is the angle of this m equal to -1 mode. Because this m equal to 0 mode, the red color one and the black color one, they have the same angle of instance, but m equal to -1 has a different angle. So you have to use m equal to -1 in order to achieve different kinds of beam manipulation. So I'm entering as -60, so minus pi by 3. Then it will ask us what are the target efficiencies. For what efficiencies you want to design a metagrading. So if I want to design a metagrading for anomalous reflection, that means incidence happening at 10 degrees, reflection happening at -60, you have to enter the efficiencies like this. So why 1 here? Because this is m equal to -1 in reflection. That's what you want here. That's why this is 1. In all the remaining 3 modes, you have to enter 0. For example, if I want power splitting, you have to enter the efficiencies like this. So I'm designing for anomalous reflection. So I'll enter 1, 0, 0, 0. Then this algorithm will run, and for optimization purpose, I have used, actually it's busy, it's running. So it will take some time. For optimization purpose, I have used two functions. One is fmincon and genetic algorithm. So before going into that, first let's see the algorithm. Then I'll come back to the MATLAB. So for this algorithm, the input is nothing but you have to decide what kind of beam manipulation you want. Accordingly, you have to give the target efficiencies. Next, what is the substrate and what is the operation frequency? And the output this algorithm will give you is the meta-atom dimensions. Meta-atom dimensions are nothing but the values of W2, W4, etc. up to W13. The remaining all dimensions you already know. What is the unit, what is the periodicity, everything you already know. Height and epsilon r2 you have to give to the algorithm. And finally, the algorithm will give the dimensions of this unit cell. So this is the algorithm which I have divided into 8 different steps. So I'll give a very brief idea. So first you have to decide the unit cell period in order to allow the required number of modes. Here I'm explaining only for 4 modes, m equal to 0 and m equal to -1 in reflection and transmission. So accordingly, you have to decide the unit cell period, Ly value. And this Ly value has some formula. For 4 modes, Ly value is different. For 6 modes, Ly value is different, like that. Then in this step 2, you have to decide the allowable range for the outward angle. So what is the range for the m equal to -1 mode? Then you have 4 modes. those 4 modes amplitudes will be written in terms of currents from I1 to I14. And by applying the Ohm's law, we can have a relation between the impedances and currents. And finally, using matrix inversion, you can have currents in terms of impedance. But here you can see Z1 to Z14, but here only 6 impedances. The reason is out of 14, 8 are unloaded. Unloaded means their impedance will be 0. So we are left with only 6. And finally, using step 5 and step 3, we can have the amplitudes in terms of impedances. So from impedance, we can calculate the capacitance, and from capacitance, you can calculate the width. Here, that means we are forming a relation between the width of the meta atom with the desired targets. When we change the width, we can achieve the desired targets. That's what we are actually doing with the help of this algorithm. So these are the results. Before going to the results, let's see whether, MATLAB has successfully completed. So now let's see what are the achieved efficiencies. So I have given 1,000. I got 0.96, that means almost 96% efficiency. And for the remaining modes, only 0%. And for these efficiencies, what are the width of the meta atom? Total 6 are there. That's why you can see total 6 values are there. They are in terms of mm. Now what I'm doing is, I want to check this algorithm, whether these are giving perfect results or not. So I'll take these values and I have entered here in the CST software. You can see this values 4.62, 6265, 0.65. I mean the same values. And then I have designed here in the CST software this meta grading. And I have got almost the same results that I've got from the MATLAB. And these are the results that I'm showing here with 100% accuracy. And these are the efficiencies for anomalous reflection, for anomalous transmission case. That means when I select instant angle 10 degrees and transmission at -45, I'm getting 98% efficiencies. And this is the meta grating exactly at the center. This is a meta grating structure where you can see this meta atoms are acting like secondary sources with red color ones. They're exciting here. And this is a specular transmission. That means we are incidenting at 10 degrees, transmission at 10 degrees. This is anomalous reflection. Incidence at 10 degrees, reflection at -60. This is a beam splitting. 50% splitting in transmission, 50% splitting in reflection. And I have checked the algorithm for different substrates and at different frequencies, and for all the cases it's working very nicely. It's working and it's giving very high efficiencies. So these are some of the test cases we have used in the lab for anomalous reflection, anomalous transmission, beam splitting, and these are all efficiencies. And for one case, that means for anomalous reflection case at 10 GHz, we even fabricated it. And you can see these are the meta atoms. They are capacitive type. And we got very good results in measurements as well as compared to the simulations. Finally, this is what I want to show you when I talk about reconfigurable meta grating. Ultimately, my goal is to replace the capacitive type meta atoms with a varactor diode. Total, we have 6 meta atoms. Here I am showing only the bottom view. That means I have only 3 meta atoms. This is 1, this is 2, and this is 3. And these extra ones are nothing but you will be having periodicity along the vertical axis. This is one more unit cell. Don't focus on this. First focus only on the top 3 ones. So total 3 meta atoms in the bottom layer are replaced with the 3 varactor diodes. And why I have used unloaded wires? What is the use of this? I have never explained here before in the PPT. The use of these unloaded wires is to provide the biasing circuitry for these varactor diodes. You can see I have a circuit here: voltage, then resistor, then varactor diode, then connection with the other one, and then you have ground. One complete circuit, and that circuit will be used to control varactor diode 2. And you have one more circuit here, which will be used to control VD4, and finally one more here. So we have total 3 varactor diodes and can be controlled using unloaded files. Coming to the advantages, I already explained here. So focusing on disadvantages, the only disadvantage or the only beam manipulation that the proposed algorithm is not giving is beam steering property. The reason is this is the formula to calculate Ly, and this Ly is dependent on theta 0 term. Theta 0 is the outward angle. So for beam steering, you want to change this theta 0 continuously. If you want to change, you have to change the periodicity of the unit cell as well. But when you fabricate the meta grading, you can't change the periodicity of unit cell. So that's the disadvantage I'm facing currently. And the other disadvantage, it works only for the TE polarization because I have selected the capacitive type meta atoms. If I select inductive type meta atoms, then it will work for TM polarization. So this figure shows the experiments conducted by the University of Surrey. This is the arrays they have developed, and here is the transmitter. This person is having a transmitter, and here is the receiver. And this particular arrays is giving the anomalous reflection, and the results are very successful. But the problem here is this particular meta grading or this particular RIS is working only for the anomalous reflection. It's not working for the transmission. It's not working for the beam splitting. It's not working for the power splitting. So as I discussed before, the RIS should achieve all these kind of beam manipulations. And as per my literature survey, there is no full-fledged RIS developed till now. If someone able to develop it, some exciting questions he or she can answer, like where should RIS be placed? Is it placed close to the transmitter or receiver or some other position? If you take a small room, how many RIS are required? And what about the RIS switching time as compared to the channel coherence time? So there are lots of unanswered questions. If someone able to develop it, so they can answer these questions, and they can bring the RIS from concept into reality. Here are the references that I have used for this PPT. And finally, I want to thank the funding agencies, SERB, DRDO, and IIITDM for funding my project works. And thank you so much for the audience for your kind attention. If you have any questions, you can please ask.
Yes, I request participants to have any question, then please post in the chat box or they can directly ask.
Please, sir, show me the references first, sir.
Can you please repeat?
Please show me the references slide.
Palas sir, your voice is breaking.
Please, sir, show me the reference slide.
Yeah, this is the reference slide.
Thank you, sir. Thank you.
Good evening, sir.
Good evening.
Sir, good evening, sir. Sir, actually, some MATLAB programming that you have shown regarding IRS, RIS. So that for MATLAB coding that you have done or the equation that is involved, if someone want to do that portion, so where to start these things? Because nowadays everyone is moving for that IRS or the reflecting surface, intelligent reflecting surface. But the idea is not that much of easy, as you have said very well, that we have to consider a lot of things, that angle of incidence and where the user terminal will be there, what angle, what strength is required. So questions is too much, but the answer is still is not available regarding where to, from how to start these things regarding designing and estimation, power estimation, channel estimation. So what is your opinion regarding this if someone want to start in that domain?
Very good question. There are actually two options. One is, first you have to decide whether you want to construct the RIS by using meta surfaces, or you want to construct the RIS using meta gratings. So the first thing you need to do is you compare the advantages and disadvantages of these two, meta surfaces or meta gratings. You look for this paper. There is this paper. You can note down if you want the reference for. This is Huygens meta surface via the equivalence principle design and applications. There they have shown how to design a meta surface for a given for a desired beam manipulation. There clearly some equations are given. You need some basics obviously to understand them, and this is a very good paper to start. And whereas if you want about meta gratings, this reference 6 is the first paper in meta gratings. Before that, we don't have any meta gratings concept. The meta gratings concept was discussed previously in 1990s. That was in optical frequencies. But in our domain, in microwave frequencies or millimeter wave frequencies, this is the first paper. So if you want to study about the meta gratings, you have to follow the first reference 6. And then this reference 6 is actually the work from Andrew Allou's group. And that work is later continued by Ariel Epstein. He is a professor at Technion, Israel. So I actually worked with him for 3 months. There I have learned from him and used that equations and develop the coding, etc. in the MATLAB. So I recommend these papers to study, especially from Ariel Epstein if you want to work on meta gratings. And recently, we have some techniques like deep learning, machine learning, etc., where they don't use all these equations. They are directly considering some kind of unit cell, and they are doing some optimization with those machine learning and deep learning, and they are directly designing the RIS. So first you have to decide which way you have to choose, whether use the equations or use those techniques. So yeah, I hope I have answered your question.
Yes, thank you, sir. I will do. I will surely, if anything will be there, I will come back. It's through mail, maybe if possible, I will connect.
Sure.
Thank you.
Yes, anyone else have some queries?
Or should I check the chat box?
No questions. I checked. Yes, you can post your queries in chat box also.
Hello.
Yeah, please.
Sir, one more request. Could you please share your PPT? It will be actually the IRS part. If you don't have any problem, actually.
Yeah. So exactly what slide you want?
No, sir. Actually, I am asking for sharing the PPTs with the participants, so the PDF copy. So it will be for beneficial those who want to do research on IRS part. So in later on.
Actually, this work currently in review, so
okay, sir. Okay, sir.
There will be conflict, right? So,
okay, sir. No issues, sir. Thank you.
Yes, so there is one question in the chat box. What do you mean by surface intelligence?
So acting according to the wireless environment. Intelligent is nothing but it's sense the environment and act accordingly. For example, let's say user suddenly moves from one position to another position. So that information will be sent to the RIS and it has to act accordingly. So it has to sense that user moves from one position to other position, and it has to shift the beam from one location to another location. And why we are calling surface? Because it's a 2D version. We don't have any 3D structures there. We are everything focused on the surfaces. All the beam manipulations that we are doing, that's focused on a particular surface. So that's why the surface name is.
Sir, one more question. Can the meta-grading concept be used for design of filters as well?
Definitely. Meta gradings are not only used for RIS. You can find some papers where meta gradings are used to reduce the reflections in waveguide bends. For example, if you bend a waveguide at right angle, so you will get there some kind of reflections. And if you want to stop them, meta gradings have been used. That's one area. And recently, one more paper have come where meta gradings are used for polarization conversion from linear to circular. So similarly, I definitely feel that meta gradings can be used for design of filters as well. But till now, there is no paper in the domain of filters. So if someone is really interested in meta gradings, she has to concentrate in this. And if you can explore this concept, and if you can write that coding part for different kinds of applications, so I'm sure that you are able to publish in a very, very good journals like IIIT Transactions. One of the why I'm saying all these things, because when I started this work and it's very new, so because of this I got lots of projects and publications. So that's what I'm saying.
Yes, Dr. Arun Kumar raised their hand. Have any queries, sir? Dr. Arun Kumar. Okay. Anyone else want to ask the questions or any query? They can ask or post in the chat box.
Unfortunately, it is actually very late night, 9 o'clock. So I don't know how many audience exactly grab the things.
Okay, sir. I think no queries from participants. So thank you very much, sir, for your informative session. On behalf of everyone here, we are very grateful for your time and insights. I think participant must be benefit from it. So can we have a photo, ma'am?
Yes, Jyoti.
Yes. So I request all the participants to switch on their cameras. Yes, Anuradha, ma'am.
Yes, yes. I hope everybody is ready. I'm taking the screenshot now. Thank you, everybody. It is done now.
Thank you, everyone. Thank you very much, sir.
Thank you so much. Okay, can I leave?
Yes, sir.
Yes, sir.
Yes, sir.
Thank you.
I request all the participants to fill the feedback link for the session 2. It is there in the chat box.
All the participants, please fill the feedback form. The link, this meet will be open for 2 minutes only.
Monali madam, can we close meet?
Now, Manisha, it's 2 minutes.
Okay.
Yeah.
मैम मेजोरिटी ऑलमोस्ट काफी रिस्पॉन्स आ
How
गए
many
हैं
responses are recorded, Chintan?
मैम 110
Just a bit. First, stop the recording. First, stop the recording. Manisha, stop the recording first.